Good morning, Astronomy 1010. Welcome to our Wednesday class where we have a lecture on timekeeping, calendars, clocks, and the moon. And then we will do our homework number 2, which I got to warn you, it's a little bit of a doozy. So hang on to your hats, okay? So let's try to get right to things, okay? I'm going to share my screen with you guys. And I think we're going to start off. I want to squeeze this in while I can. I want to do a little lecture on the phases of the moon before I get into timekeeping. I believe this will work out well, but let me, excuse me. Excuse me. Whew.
That's done.
I've got the sneezes today. Jesus. Okay. Here we go. The phases of the moon are kind of like a classic astronomy thing to do. Believe it or not, oops, I didn't learn them until I was in graduate school. And I was taught my phases of the moon not by a teacher, but by a fellow astronomy grad student who showed me a clever and cool way to learn the phases of the moon and to be able to predict the rising and setting times of the moon. I think that will come in handy during the course of our lecture on timekeeping today. It may not be obvious to you all yet, but every aspect of your day, your time, your calendars, they're all connected to astronomical objects. And so what we're going to do is we're going to have a little Bob Ross moment where we draw a picture and learn how to recreate the phases of the moon and understand the geometry of it. First thing I need to do is to hide the trolls. Hold on a second here, because the trolls are in my way. Let's hide non-video participants. Wow, okay. There we go. Now here's the real people that I can talk to for a second. All right, let's do a little Bob Ross time. Let's learn our phases of the moon. There are 8 phases of the moon, and to understand how it works, we have to start by drawing Earth. Leave yourself a lot of headroom here. We're going to be using this whole board. So somewhere in the middle, I want you to draw a circle that represents Earth, okay? First thing you got to do, if you're going to learn the phases of the moon, is you have to decide from which side of the board the sun is coming from. I, by convention, always choose the sunlight as coming from the right-hand side. So you can put to the sun. Parallel rays of sunlight are coming from the right-hand side of the plane. And that means I can draw a line in the middle of Earth that represents the daytime and nighttime side. There's a special name for this line. I don't suppose any of you know what it's called, do you? In an astronomical object, the boundary between the daytime and the nighttime side is called the terminator, okay? So we just drew in our terminator that separates the daytime side from the nighttime side of Earth. First thing to recognize is that the spinning Earth is a clock, okay? And where you are on the Earth in relationship to the sun kind of determines what time of day it is. You keep solar time. You keep time by the sun. That's how our watches are synchronized. So, for instance, if an observer was located at this little stick, if that's where the observer's meridian was pointing, this would be 12 p.m. This would be 12 noon. And pointing away from the Earth would be 12 a.m. That's midnight, okay? Here, this would be, let's see, the Earth spins counterclockwise. So if we're looking from above, from north, the Earth is spinning in this direction, and that makes this 6 p.m. and this 6 a.m. Okay, you can even throw in the extra times if you want. You can do 3 a.m., 9 a.m., and so forth. To draw the phases of the moon, we're going to draw in 8 moons. First, I'll draw in 4. 1, 2, 3, 4. And then I'll draw in 1, 2, 3, 4. Okay? All right, let's draw the terminator on each of these moons. Sorry, I'm having some difficulty with my moon here. So draw in a terminator boundary for each of your 8 moons. Then shade in the nighttime side, okay? The nighttime side is the side that points away from the sun. The sun is far, far away. So it's always the right-hand side. Now, this is what the phases of the moon would look like if you could see them from space, okay? The nighttime side of the moon points away from the sun. The daytime side of the moon points towards the sun. This is not what we see from Earth, of course. What we see from Earth is 8 phases, each with unique shadows, something a little more like this, all right? We see the moon going from crescent to quarter to gibbous phases to full, back to gibbous, quarter, crescent, and then new again. So let's go ahead and let's label in our different phases of the moon here. The moon in between Earth and the sun is the new moon. The moon opposite the sun is the full moon. Everything that's going, the moon also orbits counterclockwise as seen from north. Everything is spinning counterclockwise in space. So when the moon is growing from new to full, it's waxing. So this is waxing crescent. This is first quarter moon. This is waxing gibbous. Everything that's shrinking is waning. This is a waning gibbous moon, or Latin, or they were preserved by Arabs during the Middle Ages. Whoa. Hey, someone who's trying to watch my other lectures while watching this lecture, that's a hell of a that is a hell of a attention span operation there. But you might want to mute yourself so I don't have to listen to you trying to double fist it here. Okay, so anyways, now we go to third quarter. And lastly, to waning gibbous. Oh, I'm sorry. Well, waning crescent. I'm sorry. I got distracted there. Okay. Take a moment to catch up to me while I sip some delicious and nutritious coffee. It's important that you draw this in your own notebooks because it'll help you to learn. It's Alex and Jake, right? All right, I want to rename you guys. Alex. Just gonna check out how everyone's doing here. Okay, the goal is to try to show you how we end up getting the geometry of shadows I used to try to attempt to do it with a spotlight, but it's a little bit difficult. I wonder if I could, hold on a second, guys. I'm going to plug in a lamp here and give this a whack. I wonder, shoot. Hold on, students. I probably should try to make it darker in here. I wonder if I could reproduce it. I used to have a very bright projector in the classroom, and I could actually reproduce some of these shadows. But it's hard to get it. I have a lot of windows in here, so it's hard to get it as dark as I want to. Let's try this big one. It needs to be even brighter. Let me try one more extra lamp. I tried a little extra lampness. Now, the way you get the geometry of shadows on the moon is because the moon is a three-dimensional object, right? It has a protuberant belly that sticks out towards the observer, and yet the moon is so far away that it's basically flattened on your sky. It's a three-dimensional object that's rasterized, or it appears as a disk. And this tends to make some sort of interesting shadows, right? For instance, to see which phase of the moon you'll be in, you can imagine drawing a line through one of these phases, say here. When an observer rotates into the field of view of the new moon, they're only going to see the dark side of the moon. So you end up seeing nothing when it's a new moon because, well, two reasons. One, you're looking at the dark side of the moon, and the other reason is it's up during the day when the sun is up, so you don't see any moon. The moon is being reborn then. On the other hand, when you're in the direction of the full moon, when you're looking towards the illuminated side of the disk, you will see a complete bright disk in your sky, right? So that's sort of like when the flashlight, where's my moon here? I didn't really think this was going to work, but I decided to give it a shot. So if I illuminate from this direction, right, you can see the full disk of the moon. During the quarter phases, you can see exactly half a moon. Let me see if I can get the angle right here. You can see, this is really weird because everything is flipped around in my, like the light is there for me, but left is right in my view right now. Anyways, so you can see you have one half of the moon in darkness, one half is illuminated, and you end up seeing a disk, right? You end up seeing half of a disk. So at either of your quarter phases, what you're going to see is you're going to see a half illuminated moon in your sky. The crescent and the gibbous ones are the hardest ones to see. Imagine we were looking up towards waxing crescent right now. You would see a cross section that looks something like this, right? And so what's going on is your moon, you're seeing half of it, but 3/4 are in darkness, and this one little pizza wedge, a little pizza slice, or actually it's more like a three-dimensional tangerine slice, that's what's illuminated. But what's happening is, let's see if I can reproduce this from this side, if I can make a crescent. Turn this off. Can I make a crescent? I'm not getting a hard enough shadow because there's too much light coming from the blinds there, but basically you're getting this, you're getting a three, let me try this right. You're getting this three-dimensional tangerine slice illuminated here, right? But because the moon is flattened, you end up seeing it. Sorry, I'm doing this all backwards in my camera, so it's confusing to figure out how to move my hand. You're seeing this little crescent here illuminated. All right, this is an epic fail as a demo. In any case, if we were going to draw it on the board, what you end up seeing is what they call the fingernail moon in the Arabian Nights, right? You're actually seeing a three-dimensional wedge illuminated, but it flattens out as a crescent. Likewise, the gibbous moon, we would draw a diagonal through there. We'd be looking at it from this direction on Earth. And what you would see is you would see, so here's the belly of the moon. One tangerine wedge is in darkness. The rest is illuminated. And you end up getting that egg shape that we call the gibbous moon. So the gibbous
So it's like the opposite of the other one?
I'm sorry, Juan, can you ask that question again so I understand it?
Is that like the opposite of the waxing crescent?
Yeah, I always want to be careful, Juan, when I use the term opposite. Yes, actually, in this case, that's fair. It is it's the opposite shadow geometry, right?
Right.
I didn't draw this very well, Juan, but this is a tangerine wedge that's illuminated. This part's in darkness.
Okay.
So the crescent is a fingernail moon. The gibbous moon is an egg-shaped moon, okay? And same down here for this gibbous and for that crescent. I'm trying to just show you how all of these terminators lead to the shadows that you know when you see illuminated slices of the moon on the sky, okay? Now, this is actually a sophisticated diagram that can do many things for us. In fact, maybe I could just, let me take a second here to show you my slideshow while I fiddle with the lights. The picture that we should have in mind here, the picture that we just drew is this picture, okay? So I endeavored to show you, and I did a sort of bad job. I endeavored to show you how this moon ends up giving you the crescent, right? The trick is to make sure that you draw a line that's perpendicular to your direction of observation. An observer at 3 p.m. will see the waxing crescent moon overhead, but they're only going to see this portion here. The portion, oops, the portion that's facing the Earth. Okay, let's see if we can use this diagram to answer some tricksy questions about the moon. And I'm going to arrange my lighting here, just a second. Class, look at this diagram and see if you can answer me this question. Let's focus for just a second on the new moon. I want to know if you can tell me what time the new moon would cross my meridian. So on the day of the new moon, what time will the new moon cross my meridian? To answer this question, you have to remember what the meridian is. And I'm almost 100% sure most of you have forgotten that. So Harmony or someone just look up the definition of meridian and regurgitate that for me.
A circle of constant longitude passing through a given place on the Earth's surface and
No. The meridian is an arc on your sky, Juan.
It rises due north, reaches the zenith, and sets due south.
North, south, zenith. That's right. In other words, we better get a visual aid here, guys. Okay, wait. This is slide 78. Let me try to remember slide 78. And this, come on, baby. Wow. This slideshow is not as good as my old one. I want this one. And I want F5 slide function 47. Yeah. In other words, when the moon goes through your sky, right? Let's get some help here. The moon usually rises somewhere in the east, like here, and then it will come up and cross your meridian, and then it will set somewhere down in the west. And during its journey, it travels like this. It goes up through your sky, crosses your meridian, kind of like the celestial equator, and it comes down. So the meridian is this point here when it's at its highest, okay? This is your meridian. It's the north to south arc. The meridian is the halfway point that an astronomical object makes through as it goes through the sky. So let's get back to slide 78 here. What time will the new moon cross your meridian?
Midnight.
No.
6.
No.
9 p.m.
No. Okay, maybe I can just slow this down for you guys because there's some things that you're probably not thinking of. Do you guys know how long it roughly takes the moon to go around the Earth? How long does it take the moon to go around the Earth? Take a guess.
Like 30 days.
Yeah, that's where we get a calendar month from the cycle of the moon, right? So if you think about it, during one single day, the moon doesn't move much in its orbit. Like during the new moon is kind of pinned right there in the sky and it doesn't move. You, on the other hand, and everyone else on Earth are spinning around in a 24-hour period. So sooner or later, everyone spins into the direction of the new moon and spins away from the new moon. You always see one half of the celestial sphere in your local sky. So anybody on this side of Earth, on the nighttime side, is not going to see the new moon because it's below their horizon. Only the people on this side of Earth can see the new moon. Does that make sense? Henry kind of nodded his head, like he wants to agree with me, but he doesn't really understand what I mean. Okay, I'm used to that. All right, so fine.
Question.
Well, I'm sorry, Henry? Or Jake?
Jake.
That wasn't me.
So it's a trick question then.
No, you guys gave me answers like midnight and 9 p.m. I want to know, at what time does the new moon cross your meridian in your local sky? And clearly the answer cannot be 9 p.m. or midnight because it's not even up in your local sky. You have to learn how to answer the question. I'm doing this awkwardly, but I'm doing it. Take another guess.
Oh, wait,
Noon.
it's
Who said it? Who got it? Henry. Henry, I guess you did understand me, huh? Henry, can you explain to the class what's going on there?
Well, that would be when it's directly at like your meridian point.
Yeah,
That's
if
when it
you're
crosses.
here, it's at noon, and the meridian is your line overhead, more or less. That's when the new moon crosses your meridian. Okay, Henry Fox Hotshot, maybe you can answer another question for me, okay? Henry,
Maybe.
if the new moon will cross your meridian at noon, what time will it rise and what time will it set?
6 a.m. and 6 p.m.
Damn, he's good. Damn it. He is good. Let's write that. First of all, let me explain how we got that. Henry remembers that the Earth is rotating in this direction, and you could always see one half of the celestial sphere in your local sky. That makes this, if your head is pointing in the direction of noon, this line is your horizon line. And the leading side of the line, this is, let's see, east. And this side down here is west, right? And the line is rotating in that direction. So sort of when the line goes like this, that's when the new moon comes up over your eastern horizon. And then your horizon keeps spinning in this direction, crosses your meridian at noon. And then when this western line swings up, that's when the moon will set below your western horizon. Okay, maybe not everyone followed that, but let's write it down, okay? I need to erase this. Is everyone satisfied? Can I erase this? I'm doing it. Okay. What have we learned? The new moon rises at 6 a.m. It crosses your meridian at 12 noon, and it sets at 6 p.m. That means the new moon is up all day. Let's try another one until you get it. Full moon. Rise, meridian, and set. Henry understands, so he shouldn't answer anymore because he's not fun to play with. Okay, so someone besides Henry, what time will the full moon rise? What time will it cross your meridian? And what time will it set? Who's got this? Who's following me?
Will it rise at 3 a.m. and
No.
set at 9?
Unfortunately, no.
Will it rise at 6 a.m.?
Hold on, Bella. Remember that the Earth is spinning in this direction, right?
Yes.
If you're at
no.
6 a.m., your head's pointing here. And
Yeah,
that
okay, no.
your
Now I
meridian.
get it now.
Okay, so clean yourself up then. What should you have said?
So the meridian's at midnight
The meridian's at midnight. What time does it rise?
at 6 p.m.
That's right. Because at
and
6
it sets at 6 a.m.
Very good. So when your head is pointing at 6 p.m., your horizon goes like this, and this is your eastern horizon, and that's your western horizon, right? And
Yes.
Earth is
Same for every phase of the moon?
pretty much, right? So we'll test you again, but first, yes, you are, whoever said that it works the same for every phase of the moon, but let's do this. Rises at 6 p.m., crosses the meridian at 12 a.m., and it sets at 6 a.m. In other words, the full moon is up all night. Okay, one last test just for funsies. Let's say it's 3 a.m. and you're drunk and you're leaving the bar and you stumble out at night and you look up and in the east you see a waxing, sorry, let me try that again. In the east you see some type of crescent moon rising. So it's 3 a.m., you've just left the bar and you look to the east and you see a crescent moon rising. Is it a waxing crescent or is it a waning crescent moon?
Waning.
Waning?
That's right. Because if your head is pointing in the direction of 3 a.m., your horizon goes like this. The only moon that could possibly be in your sky is a waning crescent moon. One way I like to think about it is the waxing crescent moon is the one that you see around dinner time, right? The waning crescent moon is the one that you see if you've been up too late or you get up too early, okay? So those are some good, now you too can, and I challenge you to put this knowledge to the test. You'll notice the moon more now that you've taken this class. See if you can tell what phase it's in. Not just whether it should be obvious whether it's a crescent or a gibbous or a quarter, but challenge yourself. Say, is that a waxing crescent or is that a waning crescent? Is that a waxing gibbous or a waning gibbous? You'll notice these things more and it will make the moon your friend, okay? So a question I have is, it looks from this diagram, if I look at it here, it kind of looks like every time there is a new moon, I should get a solar eclipse because the moon will block the sun. It also looks like every time there's a full moon, I should get a lunar eclipse because the Earth will block the sun. Why don't I have eclipses every month? Why don't I only get them every year or seemingly even less than that? Shouldn't there be eclipses every time there's a new moon and full moon?
All three would have to be perfectly linear and
Okay, you're not wrong. That's right, but I need you to explain that better. Linear in what sense? And there's many directions in space, right? So Was that you? Who was that was just talking to me?
That was Noah.
Oh, hey, Noah. Noah, can you flush that out a bit?
Well, yeah. What I meant by that is you have obviously the sun, the earth, and the moon, and they would all have to be in a perfectly straight line in order for you to.
But okay, so let me be a contrarian. Aren't they? It looks like they're in a straight line here, Noah. I don't get it. Like, look, watch. I'll draw a straight line. So I'm going to play devil's advocate. So isn't this a straight line? Earth, moon, sun. You said
Right.
they need to be a straight line to have an eclipse. So. So isn't that a straight line?
Yeah, it is. I don't really know if the rays of the sun go around anything or
No. It's sorry. Okay.
Wait, it has to be against the sun. The
No.
moon has.
The trick is this is a two-dimensional image, right? The moon could be above or below the plane of this image. Maybe I can show you here. Look, if the moon, let's pretend your video camera is the sun. Where's my dumb little moon here? If the moon orbited in the same plane as the Earth and the sun, then sure enough, every time there was a new moon, this is new moon, I'd have the moon blocking the sun, and that would be a solar eclipse. And every time there was a full moon, the Earth would block the sun, and there'd be a lunar eclipse. But that's assuming that the moon orbits in the ecliptic plane, the plane of the Earth and sun. As a matter of fact, the moon's orbit is inclined by about 5 degrees with respect to the ecliptic. So it goes down below the plane of the ecliptic. There's kind of not enough room. This is easier when we're all in person. And it also comes up above the plane of the ecliptic. Like, for instance, sometimes when it's a new moon, the new moon actually sits a little above the ecliptic plane, or sometimes it sits a little below the ecliptic plane. Actually, this is one place where the book did a pretty decent job in its diagram. Let me show you a picture here. They imagine the ecliptic plane is like a sheet of water. The ecliptic plane is the Earth-Sun plane, right? And you can see that the moon is actually plunging above the ecliptic plane and down into the ecliptic plane. It's inclined by about 5 degrees, Gesundheit. So here, in this configuration, this is new moon, and you can see that it's below the ecliptic plane, so you do not get an eclipse. And likewise, the full moon is above the ecliptic plane, so you do not get an eclipse. But a few times a year, actually 2 times a year, as the moon is sliding up and down along its orbit, occasionally its orbit will shift into a position where it will cross the ecliptic plane close to the time of new or full moon. And those are times where you can get an eclipse. They're called eclipse seasons, all right? So you don't get an eclipse every month, but you do get a couple of eclipses each year. And we're just going to kind of quickly list those types of eclipses so that you guys can learn them. Six types of eclipse. So we're going to have 3 lunar and 3 solar eclipses. Okay, the first type of lunar eclipse is called a penumbral lunar eclipse. And penumbral lunar eclipses, by the way, so lunar eclipses happen during full moon, and solar eclipses happen during new moon, all right? A penumbral lunar eclipse occurs, actually, I probably should have backed up here and showed you guys a picture. There are 2 types of shadows cast by an extended object. There's something called the penumbra, which is a partial shadow, and there's the umbra, which is a full shadow. And the different types of lunar eclipses happen because the moon can sort of sit in one of 3 configurations. Here, you're in partial shadow and you get a penumbral eclipse. Here, you're in total shadow and you get a total lunar eclipse. And when you're kind of on the boundary there, that's when you get a partial lunar eclipse. So what's happening is the reason the penumbra is not a complete line of shadow is if you are sitting in the penumbra, rays from the top of the sun can penetrate this shadow, whereas rays from the bottom of the sun cannot. So only once you're in the umbral shadow are you in complete darkness. So penumbral lunar eclipses are actually a little bit of a letdown because the moon is still illuminated and you kind of have to know they're going on in order to see them. So in a penumbral lunar eclipse, the moon will go from bright to slightly dark and then bright again. But because most people only spend just a few seconds looking at the moon while they're on their way to the gas station or something, you wouldn't really know it was happening unless you stared at it for several different hours. Actually, hold on, class, can you just give me, oops, resume share. Okay. Class, just pause for 1 second. Still recording, okay. So we have a penumbral lunar eclipse when the moon enters the penumbral shadow. We have a partial lunar eclipse when the moon is on the boundary between the umbra and the penumbra. That's where you actually start to see a bite getting taken out of the moon. So during a partial lunar eclipse, you can actually see the Earth's curvature as a shadow that kind of takes a bite out of the moon. And then lastly, when the moon goes entirely into the umbra, that's when you get the coolness that is a total lunar eclipse. You would think the moon would go completely dark during a total lunar eclipse, but it turns out that the atmosphere of Earth kind of works like a lens. And maybe this is what you were thinking about earlier, Noah. Light can bend around the curvature of Earth by passing through the atmosphere, and that light becomes filtered and it becomes reddened, and the red light bounces off the moon to give us a total lunar eclipse. Let me explain that a little bit better here. So I want to show you that picture of the umbra again. Slide 81. If Earth had been an airless rock like the moon or like Mercury, during a total, excuse me here, I'm just getting a circle. During a total lunar eclipse, the moon would be in the umbral shadow and all of the light would be blocked and it would go dark. But it turns out that the Earth is surrounded by this thin, fuzzy atmosphere, which kind of works in a similar way to glass in that it can bend sunlight. So light from the sun strikes the atmosphere, but then it becomes reddened as it passes through the atmosphere, and it bends around the Earth, and a little bit of sunlight, a little bit of red sunlight leaks through the atmosphere, bounces off the moon, and then bounces back to Earth. And this is why during a total lunar eclipse, when the moon enters the totality phase, it develops a sort of evil blood red color that terrified ancient peoples. Sometimes you can find really nice time-lapse photographs of a total lunar eclipse online. There's kind of a cottage industry of photographers who try to get a cool time-lapse of a total lunar eclipse. There should be a few up here, but let's see if we can just find a nice one. I like it when they show the moon kind of doing this, like this. This would be an okay example, but I've seen better ones. Yeah, this one I've seen before is totally wild. I think this is a fantastic image. So they've taken a picture of a lunar eclipse over some town or some set of mountains. Sorry guys, I'm trying to, Control plus, there we go. It's not as high resolution as I would like it, but you can, hold on a sec, let me, okay. You know what, this picture is too low resolution for me. Let's do one last thing here. Oh, here we go. Yeah, this is what I'm talking about. This is the good stuff right here. Okay, check this out, guys. You can see the moon first as it goes into totality. First, you see the full disk of the moon. That's actually probably in the penumbral stage, but it's hard to recognize it because it's just a little bit darker than usual. Here you can see the partial eclipse starting, where the shadow of Earth is taking a bite out of the moon. And then when it enters totality phase, believe it or not, these moons here are actually quite a bit darker than these moons up here, but you can see that evil red color as it goes into its totality phase. And then it slides back out into a partial eclipse and goes full again. They also got some lightning and some mountains. This is a class act right here, just a totally wild looking picture. Doesn't even look real. That's going on the binder of your Trapper Keeper next semester, okay? So anyways, now you know your 3 types of lunar eclipses. Let's take a quick peek at the different types of solar eclipses. By the way, I noticed in the chat log, someone mentioning the recording. I should have been recording the first part of this. I just paused it when I had to run away for a second. Hopefully this whole thing is being recorded for the night class. This is a very interesting picture. This picture shows you a solar eclipse, all right? And it's seen from the International Space Station. And right away, you can understand why it's more rare to catch a solar eclipse than a lunar eclipse. The shadow of the moon on Earth does not cover the entirety of Earth. So if you're standing here or here or here, you have no idea that there's a solar eclipse going on. Only if you're located here, which is the umbra, and you can see there's a kind of grayish area there, there's the penumbra. Only if you're in one of these 2 spots are you going to see a solar eclipse. Here, you'd see a total solar eclipse, and if you're in the penumbra, you'll see a partial solar eclipse. And this spot will kind of move across the Earth in a complex way, so that you have to be in the path of totality if you want to catch a total solar eclipse. The 3 types that we have are the partial solar eclipse, the total solar eclipse, where you get the totality phase where the sun is completely blocked out, and then you get the annular eclipse. We did this in our homework. Do you guys remember what the annular eclipse is? What happens during an annular eclipse?
There's a ring of the sun that appears around the moon.
Good, Nicole. Do you remember why you see the ring?
I can look through my notes. 1 second.
No, that's okay. I'll just tell you. So an annular eclipse is basically a total eclipse. It's just that the moon's orbit is not a perfect circle, right? If this is the Earth, the moon comes close to and farther from Earth. If you should have an eclipse when the moon is in what's called apogee, the moon will be a little bit farther away and its angular size will shrink a tiny bit. So if the total eclipse was happening at any of these points, the moon's disk would block the entirety of the sun. But when the moon is at apogee, its angular size shrinks to like 0.48 degrees or 0.49 degrees, something like that. And it's a little bit smaller than the ½ degree angular size of the sun. So total and annular are kind of the same. It just depends if the moon is like near Earth or far Earth. Of course, during the totality phase, if you have a total solar eclipse, they look particularly wild because during a total solar eclipse, the disk of the moon blocks the disk of the sun, and you can now suddenly see light from an outer wispy layer of the sun's atmosphere. This layer of the sun is called the corona, and it's normally not visible to your eyes if even a little bit of the sun's disk is peeking out. This sunlight from the disk is so much brighter, it drowns the corona out. But during a total solar eclipse, you can see this wispy outer atmosphere of the sun. We're going to study that at a later point in this class. One last thing for fun. Have you ever seen this before? Let's look at a waxing crescent. This is just kind of for fun, but something you might be interested in. Have you ever looked up at the moon at night and saw, I'm trying to find a picture that captures it here. They usually have one or two. That almost gets it. Yeah. Okay, this is kind of it here. Have you ever been out at night and seen something like this, where you can see the crescent moon, but you can also see the dark side of the moon? How many people have
Yep.
noticed that before?
Yeah, I've seen that.
So what's
I've seen
going on there? Why can I see the dark side of the moon in this instance?
The moon's being hit by the sun's actual line of sight. What do you call it?
I would have to dispute that with you. It's that doesn't make a ton of sense, because as you saw from our drawings, the sunlight is hitting this portion of the moon.
Yeah, it's also going through the umbral, which because the Earth is also has the shadow on it, so it's also the Earth's shadow is hitting the moon, but unless I'm thinking of partial or penumbral.
No, I'm sorry. I would, if I had to be technical, I would dispute that too. The Earth's shadow is not hitting the moon here. This is not an eclipse. Remember, let me walk back there for a second. That was a crescent moon. The Earth's shadow is not hitting this at all, because the sunlight, where's my annotate picture here? The sunlight is coming from here and from here, and we're seeing a cross section like this. So whoever I was just talking to, that doesn't make sense. The Earth's shadow is not in the way of the moon. The moon is off to the side. We need a better explanation than that. How do you end up seeing this part of the moon from Earth over here?
Light from the Earth.
Oh, wait, who said that? What did you say?
Henry.
Henry, what did you say?
Like light is coming from the Earth, from the sun. Like,
Okay, yeah. Keep working with me here. Keep talking. Explain this.
I don't really know. It's bouncing off, hitting the dark side. I don't know.
Yeah, as a matter of fact, you're right. What's happening is, believe it or not, Earth goes through a set of phases from the moon's surface, just like the moon does. You're seeing light that's scattered off the bright Earth and then is scattering back to the moon and then scattering back to us. It's what the Germans call the Gegenschein, or the against light. So when you see this, where's that picture here? You're seeing the illuminated Earth light. Now you guys know that when the moon is full, right? The full moon is bright in your sky. You can go camping during a full moon and you can see your shadow from moonlight in the forest. Let me show you a really iconic picture called Earthrise. This was a picture taken during the Apollo landing series, or the Apollo exploration of the far side of the moon. And one of the astronauts took an image of Earth. Oh God, no, I don't want this. Oh no. I just want Earthrise images. Basically, the person was in one of the orbiting capsules and was taking photographs of the moon, and he suddenly looked over and saw the Earth. What phase, what shape or geometry is this here? What phase is this?
The waxing gibbous.
Some kind of gibbous is probably waxing, but yeah, so you can see a gibbous phase, right? And this waxing gibbous Earth is rising above the horizon of the moon. And people realized that this was a profoundly cool picture for a couple of different reasons. It was the first time human beings had ever seen their planet rising up above some alien surface or alien terrain. And that was kind of a profound moment for humanity, because suddenly their Earth was not this kind of endless garden of delights that they could abuse and pollute to the heart's desire, but it was a sort of fragile orb floating in big darkness of scary space. And people actually tie the beginning of the environmental science movement, where people worried about issues like global warming and climate change, to the publication of this photograph. Also, let's just think about it from a technical point of view. What is the angular size of the moon in our sky, students? That's something you're supposed to know. What is the angular size of the moon?
0.5 degrees.
0.5 degrees. If the Earth's diameter is 3 times bigger than the moon's diameter, what should be the angular size? Wait, it's 6,400 kilometers versus 1,700 kilometers. We're going to need our calculators at some point today, so 6,400 divided by 1,700. Yeah. Oh my gosh, it's 3.76. The Earth is almost 4 times bigger than the moon. So what should be the angular size of the Earth if you're standing on the moon's surface? If I'm a dude here standing on the moon's surface, what would be the angular size of the Earth?
Like almost 2 degrees.
Just think about how freaking crazy that is. You can already see the moon like a big glowing disk in your sky. If you were standing on the surface of the moon, the Earth would look huge and it would be wicked, wicked bright in your sky. You would definitely be able to see the surface of the moon from shining Earth light. Anyways, those are some fun things to think about, okay? Okay, I'm putting the phases of the moon and the eclipses to bed. I spent way more time in that than I wanted to, so I apologize. Let's get on to some stuff that we're going to need for our homework today, okay? For our homework today, we're going to have to learn a little bit about timekeeping and the motion of the sun. So let me start off by saying that there are 2 types of day, okay? How do I want to do this? Actually, before I tell you about the 2 types of day, let's just first talk a little bit about solar time. You keep time by the sun, okay? And the idea is that the sun will travel through your local sky and you will set your clock based on that. Let's look at a picture or 2 from my slideshow. Here's a picture showing you how the sun travels through the local sky for an observer in Rhode Island, okay? Depending on what time of year it is, the sun will rise, let me choose a better color here. The sun will rise somewhere in the east. It'll come up through your local sky. It will cross your meridian at noon, and it will set down into the west in the afternoon. We owe our timekeeping systems to the Babylonians. Babylonian astronomers would track the motion of the sun through the sky. And they basically divided the day up into 2 different parts. There's an AM part. AM means ante-meridian, before the sun crosses your meridian. And then there's a PM part of the day. That's post-meridian, when the sun crosses your meridian, all right? We've designed our clock so that it's 12 noon when the sun is at the meridian. It's usually somewhere around 6 a.m. when the sun rises, 6 p.m. when the sun sets, and we reset the day when the sun is at the lowest point. I'd want to say in your sky, but the sun actually isn't in your sky. It's crossing this opposite meridian that goes below the Earth here. When the sun crosses this lower meridian, that's when it's 12 a.m. or midnight, and we reset the day. So we keep our clock by the motion of the sun through our sky. Before mechanical clocks existed, we kept something called apparent solar time. And apparent solar time is time by a sundial. This stick, which is called the gnomon, would point towards Polaris, or the North Celestial Pole, so that when the sun was on your meridian, when it swung up to its highest point in the sky, it would cast a shadow on the gnomon that would be right here at 12 p.m. So this basically just tracks the motion of the sun through your sky. And early timekeeping devices kept something called apparent solar time. Apparent solar time is time by a sundial. This is a simple way to keep time, and anyone with a little sundial in their garden can do it, but there's a problem with it. The problem is that the sun does not keep a constant rate of rotation through your sky over the year. The sun travels at slightly different speeds through the sky over the year. There's several different ways that you can see this. Ava, I'm sorry, what did you say? Oh, you can't read what's on the board. Is it because I'm in the way, Ava, or what? Can you read it now, Ava? Give me some feedback, buddy. The picture is not clear. Does anyone else have that issue? I think that's your internet connection, Ava. Can you guys read the board? Is the picture not clear for you guys as well? Harmony,
I'm kind of having that issue, but I think it's because it's on my phone, so the picture is small. But I'm just taking a screenshot and zooming in on my camera roll.
Jake, are you having that issue?
Fine for me.
It's fine for Jake. Andrew?
Fine.
Harmony? Okay, look, I think that's your internet, let me know, can I read something off for you? It looks clear for Kevin. The sun travels at slightly different speeds through the sky over the year. I'm sorry, I wrote that kind of badly too. Look, don't worry about this, okay? This is not important. Apparent solar time is time by a sundial, okay? Maybe I can work on my focus here. Logitech, okay. If I turn on my Logitech camera, it should turn off autofocus. Maybe that's contributing to this. Okay, hopefully that fixes things a bit. We can also keep, okay, so I'm getting a little distracted here, but let me show you what's going on. I want to show you guys a famous picture known as an analemma. In this picture, an astronomer has taken several photographs. They've composited several photographs of the sun at noon over the course of 1 year. Okay, hold on just a second, guys. Hey, can we kill the whistling? Yeah, it's not helping me. Okay. You can see that this photographer has captured the sun at 12 noon every 2 weeks or so for the course of a year, or every other week. And you'll see that not only does the sun rotate at different rates through the sky, because sometimes it's traveling higher through the sky and sometimes it's traveling lower through the sky. But even though they attempted to take the picture at noon, the sun was sometimes a little bit ahead of the meridian at noon and sometimes a little bit behind the meridian at noon. And there's a couple of complex reasons for this that I kind of don't have time to go into. One of the reasons has to do with the fact that the Earth's orbit around the sun is not a perfect circle. So the Earth's traveling faster at certain times of the year than at others. and that works against the length of a day. Another reason is that if you are at the spring or fall equinoxes, the Earth has this geometry with relationship to the sun, and that gives the sun a sort of north to south component in its motion during the course of the day. And in other words, the sun will travel slower through the day. If the sun is traveling through the sky during the, let's see, this would be the summer solstice, the sun travels completely east to west. Look, I didn't do a good job of explaining that. The problem is the details of it are complex, and I'll have to spend 15 minutes explaining it, and I kind of don't have those 15 minutes. So you just have to trust me that the sun rotates at slightly different rates through your sky during the course of the year. Because of that reason, people discovered that rather keeping time by a sundial, it made a lot more sense to keep some kind of mechanical solar time, time by a clock. And that's actually somewhat complicated because you actually have to calculate the average rate that the sun travels through your sky. So today, you do not exactly keep apparent solar time. You do not use a sundial, but you keep something called mean solar time. Mean solar time also tracks the sun, but it performs a slight calculation so that the length of an hour and the length of a day stay the same every single day throughout the year. Mean solar time is time by a mechanical watch. These two things are very close to each other, okay? They're close, but they're not exactly the same. So you're keeping mean solar time on your clocks, and you're keeping time by the sun. But it turns out that there's actually two types of day. There's a solar day and there's a sidereal day, and we need to take some notes on them because they show up in our homework. Okay, two types of day. There is a solar day, and that's the normal 24-hour day. This is where you, it's basically the time for the sun to orbit the sky. And then there's another type of day called a sidereal day. The sidereal day is slightly shorter. The time it takes Earth to spin once on its axis, you've been told is 24 hours, and you've been lied to. The actual spin of Earth, the time it takes Earth to do a 360 revolution, is 23 hours and 56 minutes. It's 4 minutes shorter. The sidereal day is the time for a star to orbit the sky. Sorry, Ava, you're probably having a hard time reading that. Time for a star to orbit the sky. Okay, let's take a look at why this happens. A diagram would be helpful here. Okay, Earth in the first picture is sitting in this configuration, and a local observer stands where the arrow is standing, and you know it's noon because their meridian is pointing towards the sun. Imagine that the Earth is spinning counterclockwise, and it's orbiting the sun counterclockwise at the same time. Earth is going to go through a rotation where the arrows as it's spinning, well, let me draw a couple of Earths in to try to show you what's going on here. Here's a couple of Earths, right? And as the observer is kind of flying around with the Earth, you'll have their arrow point down here and over here. In fact, you know what? This isn't going to be clear. Let's try to make a diagram together on the board. I think this will be better. I'm going to erase this class, so speak now if you have any issues with this. Let's try to draw a diagram showing why the solar day and the sidereal day are different. Start by putting the sun here, and start by putting the Earth here. And let's draw an arrow pointing to 12 p.m. Now, let's draw the Earth in these configurations. 1, 2, 3. Actually, I'm going to lower this a little bit. Sun, Earth, arrow, 1, 2, 3, 4, 5. Okay? Earth is orbiting the sun counterclockwise, and it's spinning counterclockwise. So imagine what will happen to this observer's arrow as it rotates around. So we're starting off here at 12 p.m., that's noon. In the next configuration, the arrow will point down because the Earth is rotating like so, right? Then it points to the right, then it points up, then it points across, and then it rotates a little more and it points back to the sun. Let's label these 1, 2, 3, 4, 5. Ask yourself, class, in which number 1, 2, 3, 4, 5 does the Earth complete a 360-degree rotation?
5.
No.
Oh, wait. 4, because it's
3.
Right. Kevin says 4. And that means this is a sidereal day. A sidereal day is always the true 360-degree spin of Earth, right? And the sidereal day takes 23 hours and 56 minutes. So you've been told that the Earth spins on its axis in 24 hours, but that's not really true. The Earth spins on its axis every 23 hours and 56 minutes. You actually have to, you've rotated out of the direction of the sun, and now your arrow is not pointed back to 12 noon again. You actually have to rotate an extra degree to get this arrow to point back towards the sun. And this, position number 5, is a solar day, which is 24 hours. That means there's a small discrepancy between the length of a day by the sun and the time it takes Earth to rotate.
I have a question.
Yeah.
Why do you think they told us that it was 24 hours instead of 23 hours with 56 cents?
Because,
I mean, not cents, minutes.
Since it's only off by 4 minutes, they're close enough to the truth. And because, one, think about how long it took me to explain this to you. It took me like 10 minutes to explain this to you, and I didn't do that great of a job at it either, because I'm a little distracted right now. So this, it's a complex thing to explain to people. I guess you have to learn about it in your astronomy class. That's why you're taking my class.
Okay.
They tell you, you know what the real reason is, Juan?
What?
Because nobody gives a shit about the stars. That's the real sad reason. Nobody cares about the stars because it doesn't make them any money. And most people are just concerned about whatever makes them money. Luckily for me, stars equal money, so I get to do both at the same time, right? So, anyways, before you think I'm that noble. So anyways, people don't really care about how long it takes a star to rotate around the sky. They do care about how long it takes the sun to rotate around the sky, because if you're a farmer, you have to wake up and you plant your crops. And if you're going to do a construction project, you want to be hammering nails into a roof during the day so you don't fall and kill yourself, right? People do care about the sun because our lives deeply depend upon the sun in a number of complex ways, most of it from agriculture, right? But people don't care about the rotation of the stars. So we set our clocks to be a 24-hour day because that's the time it takes the sun to rotate the sky. The fact that the actual spin of Earth is 23:56 minutes, nobody cares because not many people are keeping track of stars. That's the sad answer to your question. But you care because you're learning about astronomy. Okay, in fact, I need to get to this before class ends. One of your most difficult problems that you're going to do today involves a complicated concept called sidereal time. I think I can squeeze this in here, but it's going to be ugly. It is possible to keep time by the stars instead of by the sun. And I'm going to show you how we solve those problems, but let me erase this and let me set this up on the board for you. It occurs to me after I started this class today that I really made a big mistake by covering the moon. The moon takes a really long chunk of time to cover, and I should have waited until next class to do it, but I thought I had time to burn, so I kind of messed this day up a little bit. But we have time for one more big module, and we're going to need it for our homeworks today. It's called local sidereal time. And local sidereal time is basically keeping time by stars, not the sun. That's not the technical definition, but that's the concept, okay? Local sidereal time, which I will abbreviate LST, has kind of a confusing definition. The definition is that it's the hour angle of the spring equinox, where I've introduced a new term called hour angle. I will abbreviate it HA. An hour angle is the time since the meridian.
What does LST mean? Stands for?
Local
Okay.
sidereal time.
Okay.
HA stands for hour angle. We're also going to need to relate this to the right ascension, the coordinate that stars keep. We learned about this in our last class. Guys, this is going to seem a little nutty the first time around, but just go along with it, take the notes, and you'll start to understand eventually. Remember that last class we learned about a coordinate called right ascension. I'm going to abbreviate right ascension as RA. And right ascension is defined as the hours measured east of the spring equinox. Why don't you just start by getting all that stuff down, and then I'm going to draw a picture explaining how all this stuff works. But I need you guys to have those definitions written down. Okay, students, can I erase these definitions? Adam, you cool? All right, all right. All right, good. I was just trying to give you enough. Oh, so Ava, finish up and let me know. Thanks, Cam. Ava, when you're ready, let me know, please. Sure. All right. Let me show you how we're going to solve problems in sidereal time. Local sidereal time is going to be one of the most confusing things that I teach you all semester. So I want you to really stretch your minds here. I know you're getting fatigued, but here's how we're going to solve some problems in local sidereal time. We're going to draw a diagram of our local sky. You'll remember that in a previous class, I taught you how to make a two-dimensional view of the local sky. This time, it's going to be an east-west local sky instead of a north-south local sky. Leave yourself a lot of headroom and draw a line maybe 12 centimeters on the page. Mark the midpoint at 6 centimeters. Draw a vertical line and draw the best dome that you can draw with a free hand. Okay? Label this side as east and this is west. This is very important, students. Always put east on the left side and west on the right side. Why? Because we are going to watch stars rotate across our sky. And it's going to be like a giant clock. You want the direction of the sky's rotation to be the same direction that you're used to a clock being kept. Otherwise, you're going to get very, very confused. Okay. This line is your meridian, not your zenith. Mark it with an M. Why is that line your meridian? Let me show you a picture explaining why. Bloody hell. In this slide, it's 79. Stars can rise or set along tracks of constant declination. So they can rise somewhere in the east, they come up and cross your meridian at their highest point, and they set in the west. There are a few stars which might actually cross your zenith, but for the most part, stars kind of come up in the east and they just cross the meridian at their highest point. So the picture that we just drew is kind of like a slice of the sky that's at an angle like this. Because this is three-dimensional, we're going to watch stars rise in the east, come up and cross our meridian, and set in the west. So this is the direction that the sky is rotating, okay? The sky is rotating east to west. I'm going to take a blue star, and I'm going to put it here about 15 degrees to the right of my meridian. I'm going to draw a line from the observer up to this star. Class, if I tell you that this star is 15 degrees off from the meridian, how long ago did that star cross my meridian? Oh, I thought you would know this. Well, I could have made that angle a little better, but what is, how many hours does 15 degrees correspond to?
1 hour.
Okay, that means this star crossed your meridian 1 hour ago. And that is your hour angle. Your hour angle is your time since the meridian. The whole idea behind local sidereal time is that local sidereal time is not keeping time by the sun, and it's not going to keep time by any particular star. It's going to keep time by a point called the spring equinox. You'll remember that the spring equinox is a point in your sky, and it's located somewhere near the constellation Pisces. I had a picture of it back here. Yeah. Here's the spring equinox. It's just a random point in your sky somewhere near the constellation of Pisces. let's imagine right now that my spring equinox, which I'll do in green, is located somewhere over here. That's the spring equinox. Can you guys guesstimate for me the hour angle of the spring equinox in this configuration? Give me a reasonable guess. As to the hour angle of the spring equinox.
Dragon cheese.
4 hours.
Who said that?
1.
4 hours. This is the definition of local sidereal time. Local sidereal time is the hour angle of the spring equinox. Basically, instead of keeping time by the sun, we're going to keep time by the motion of the spring equinox through our sky. The only thing weird is if you keep a 24-hour solar clock, what does 0-100 hours correspond to? In military time, 0-100 hours is what time?
12 a.m.
Right. And that would be when the sun is like down here at its lowest point in the sky. When we keep local sidereal time, 0-100 hours occurs here when the spring equinox crosses your meridian, and then we go around the clock in a 24-hour clock. Now we estimated that this was 1 hour. The local sidereal time is 4 hours. And we can also put the star's right ascension onto this diagram. The right ascension, you'll remember, is the hours east of the spring equinox. East means counterclockwise in space. So I would start here and go back to the star. That's the right ascension. What would you guys guesstimate as the right ascension in this configuration?
3 hours.
Say it louder.
3 hours.
3.
3 hours. You just did a very important math problem, although it didn't seem like math because it was obvious. And you've just arrived at a critical formula that you're going to need for your homeworks today.
Wait, how do you get to 3 hours of the other
Okay,
one?
sure. We decided that this star was 15 degrees away from the meridian. And that means 15 degrees, the sky rotates 15 degrees per hour. Remember, 360 degrees over 24 hours is 15 degrees per hour. So I told you the star was 15 degrees off from the meridian, and that means it crossed 1 hour ago.
Mhm.
Someone else in class guesstimated that if it's 24 hours around the clock, and from there to there is 6 hours, that the spring equinox was currently about 4 hours. So this is 4 hours, that's 1 hour, 4 minus 1 gives you 3.
Gives you 3. Got it.
Okay, hopefully I explained that good enough.
Yep, thanks.
Okay, we've just derived a very important formula. The hour angle of a star is the local sidereal time minus the right ascension. I have a nickname for this formula. I call it Ha equals list minus Ra. Now, if I were you, if I were a student, and some professor had just put all this up on the board, I would probably be thinking, what is the fucking point of all of this? Because this doesn't make a lot of sense and I don't get it. The point is, if you go to a telescope and you're planning a night of observations, or you want to know when stars will be up, you can get in the habit of keeping local sidereal time, and you can quickly guesstimate when a star will rise and set and when it will be best observed. You may not think that's very interesting now, but if you ever get into astronomy and you have your own telescope and you want to look at the stars, you will start to see the wisdom of it. If nothing else, it helps you become conscious of how arbitrary it is that we keep time by the sun. I want you guys to understand during the course of this lecture that all of our calendars and timekeeping are intimately connected to the rotation of the sky. We decided to keep our clocks by the sun, solar time, but we could have equally done it by stars or by the spring equinox. Now, I had some more stuff to do during this lecture, but I honestly kind of botched this lecture by starting with the moon. I should have never done that. Luckily, I did manage to cover all the material you need for about 4 of our homework problems today. One of the homework problems I'm just going to kind of help you get through. It involves a formula on synodic versus sidereal time, which I'll explain to you when we get there. So why don't we do this, class? We're at 1 o'clock now. Let's take a 10-minute or so recess before we begin our homework. Does everyone like that idea? All right, seems that's a popular idea. So we're doing homework number 2 today. We will pause there and then we will crash through our homework as best we can. Today's homework is a bit of a whooper, so hang on to your hats. I'll see you guys in a few, okay? Welcome back, Astronomy 1010, to our homework number 2 session. We're going to crank out a serious homework today. We have our name on the sheet, AS1010, whatever your section is, 001, 002, 101, whatever you are. And let's go to our homework session, and I believe we're working on chapter S1 problems. Chapter S1 is a special chapter that follows chapter 3. If I pop over to Blackboard here, you guys can actually see the questions in our homework. What's that, Andrew?
I know the questions. It's 38, 41, 47, 51, 53, A, B, C.
Well, wait, slow down for me, homie. 38, 41, 47. Keep going, Andrew.
51 and 53, A, B, C.
Andrew, you seem to be on the ball. Do you have the questions there in front of you as well?
Yeah.
I provided them. So why don't you read me S1 number 38?
S1 38.
By the way, I don't know if I said this last time, but a few students did like some creative things during their homeworks that I didn't appreciate. Don't be creative. Put on your page what I put on my page, okay? Especially if I show work, if I show a calculation, of course you are obligated to show that calculation as well. Don't make me hunt you down, okay? I'm showing you how I want it done, and you're just, all you gotta do is follow my lead here. Okay, Andrew, read me the title of the question.
All right. Opposite rotation. Suppose Earth's rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day? Explain.
Sidereal. Sidereal means with respect to stars. Okay, so let me translate this. Earth is undergoing an opposite rotation. The spin of Earth is clockwise, the orbit of Earth is counterclockwise. First of all, I've got to judge what you guys know. Which one of these is normal and which one of these is new?
Counterclockwise is normal, right?
That's right. So we basically reversed the spin of Earth. Normally the spin of Earth is eastward, like this, with everything moving in the direction of Rhode Island, but now we're spinning backwards. I think we should start by making a diagram here and trying to understand what's happening. let's start by leaving a lot of room, and let's put the sun down here. And here's Earth, and the arrow represents a local observer's meridian pointing towards the sun, so that would be 12 p.m. And I'm going to draw in 1, 2, 3, let me try that again. I want 5 Earths. 1, 2, 3, 4, 5. Okay? We're still orbiting counterclockwise, right? That's what's up. The orbit is still counterclockwise. But we want the spin now to be clockwise. So which direction should I draw the arrow in the next frame? Which direction will the arrow point?
Up.
Up. Very good. Someone understands me. Let's label them. Let's label them 1, 2, 3, 4, 5. Which direction should the arrow point in frame 2?
Left.
Not left, because then it would be going back again, right? That's, if I go from here to the left, that's counterclockwise. Right.
Then right.
Good. What about in frame 3? Down, says Kevin. Kevin's with me. Okay, Kevin, what about frame 4? Yeah, Kevin, if we go in quarters, it would go to the left. But between 3, which is down, and between the left, I first have to go towards the sun. And then I can go left. Right, says Kevin, or rather left. Anyways, one of these numbers, 1, 2, 3, 4, 5, represents the solar day. Which one of these numbers represents the solar day? What's the solar day again?
4?
I'm sorry?
3?
Oh no, it's 5.
I heard 5 different answers there.
The solar day is the 4th. Number 4.
Is that Bella?
Yeah.
Bella is correct. This is the solar day. How'd you know that?
It's pointing towards the sun.
Exactly. The solar day is the time for the sun to orbit the sky, to go from 12 p.m. Well, I don't want to say 12 p.m. anymore because things are weird now, but that's when we're back to noon. This is what we would call noon because it's pointing towards the sun. All right, so which one represents the sidereal day?
5.
That's right. How do you know it's the sidereal day? How did you know 5 is the sidereal day? What's the logic?
Is it rotated the whole 23 and 56?
No, not 24.
No, 23. I said 23. It's like it goes back into the same position it was when it originally first started.
Yeah, okay. There's 2 things to realize here. Something I didn't tell you that I should have had you write down earlier, but I got a little distracted, is the sidereal day is always the true 360-degree spin. The word sidereal means with respect to the stars. And the stars are much further away than the sun is. So believe it or not, this arrow here and this arrow here, both of those arrows actually point to the same distant star. To understand why that is, I might have to redraw this to scale on my whiteboard here. Let me see if I can do this right. The orbit of Earth is really tiny and insignificant in comparison to the stars. So here's the sun, and here's the orbit of Earth in comparison. And the stars are like really, really, really far away. Like here are the orbits of the stars, right? So it kind of doesn't matter if the Earth is here in its orbit or here in its orbit. The stars are so infinitely far away that both of those arrows kind of point to the same star, which is here, right? Whether the Earth is there in its orbit or whether the Earth is there in its orbit, both those arrows point towards the same star. But as you can see, the sun is a lot closer. So it does matter if the Earth moves a little bit through its orbit, pointing to the left will no longer point towards the sun. So this arrow points to the sun. This arrow does not point to the sun. Both of those arrows point towards the same star. In other words, the sidereal day is the time for a star to orbit the sky. The solar day is the time for the sun to orbit the sky. Another way to think about it is the sidereal day is the true 360-degree spin of Earth. Okay, we need to read the question again. Andrew, read us the question again. By the way, I expect to see this in your homeworks, okay?
All right. So what would the solar day still be longer than the sidereal day? Explain.
The question is, if Earth now spins clockwise, will the solar day still be longer than the sidereal day? What is the answer to the question? Oh, you guys are scaring me.
I want to say no, but I'm not sure.
It's no, because the solar day comes first before the sidereal day.
Who said that?
Morgan. I didn't know if you wanted Andrew to answer it, so I would have answered it sooner.
No, Morgan, no, oh, sorry, just anyone. Morgan, you did right. You said exactly the right thing. Morgan is pointing out, hey, look, the solar day happens first and the sidereal day happens second. That's different than how, all right, Morgan, since you're so good, how long does a solar day usually last?
24 hours.
How long does a sidereal day usually last?
23 hours, 56 minutes.
Are both of them going to change? How is this going to work now? How long will the
solar day should be 23 hours and 56 minutes now.
False. The rate at which Earth is spinning has not changed. The direction has changed, but not the rate. So think a little clearer about this, Morgan. Revise your answer.
So the solar day is still 24 hours.
We artificially made the solar day 24 hours. What does not change is the spin of Earth. How long should a 360-degree spin of Earth take?
24 hours.
False. That's not how long.
I mean 23 hours and 56 minutes.
Is that going to change just because I changed direction?
No.
All right, so try again, Andrew. How long will the solar day take now? In other words, the sidereal day is going to stay 23 hours and 56 minutes. The only difference is now the solar day happens 1 degree before that rather than 1 degree after that. Have I lost you, Andrew? I'm sorry, Morgan. Morgan, did I lose you?
Wait, it's not 24 hours, right?
It can't be because it's happening before 23:56.
So 23 hours?
That's too much. Normally, in a sidereal day, let's look at the normal case again here. Oh, shoot. Stop share. Hey, Brendan knows what's up. Brendan, why are you so smart? Why were you born that way? See, Brendan's figured it out. He's figured out that normally, in a normal sense, the Earth spins 360 degrees in 2356, and it tells us in the book that the Earth has to rotate 1 extra degree to point back to the sun. 1 degree corresponds to 4 minutes, so it happens 4 minutes later. And the Babylonians and the Egyptians decided that the day would be 24 hours. They didn't give a shit about the stars at that time. They couldn't actually measure this difference. They didn't have careful enough timekeeping devices. But now, the Earth still spins in 2356, but in our present case, you end up pointing to the sun 1 degree before. It doesn't look like 1 degree here because we drew this diagram exaggeratedly, but it's 1 degree before it rotates back. And 1 degree should then mean 4 minutes shorter, 2352. In other words, the sidereal day has stayed the same, but now we would point to the sun 4 minutes earlier. Now, Morgan, yes, we have pegged our sun to be a 24-hour clock. Had the universe been born this way, the Egyptians would have called this 24 hours, and then we would have ended up with a longer one. But it's important to realize that if it switched today, it would still be 2356. It's kind of a semantics thing, if you can follow me there. Let's try to put this into a paragraph form. Right along with me. If Earth were to spin clockwise, while continuing to orbit counterclockwise, then no, a solar day would not still be longer than the sidereal day. In fact, what we proved, the solar day would be shorter by 4 minutes at 23 hours and 52 minutes. The last part of the question asked why. Does anyone think they're good enough to look at the diagram and put that into words? This will be a very hard task for you guys. What's the easiest way to describe why with those rotating arrows? How do we put that into words? Morgan, can you explain it?
Wait, I got a question. What is that word next to longer?
That word?
Yeah.
Than.
What?
Or
And?
It's actually than, Ava.
Than.
Than.
All right.
Sorry.
Thank you.
I think that's proper grammar, right, Ava? Than rather than then. Longer than the sidereal day. That's how I speak anyways. I'm not good enough at English to explain why it's than rather than then. I just know it's than. I don't know if it's the pluperfect or whatever the hell it is, you know. All right, I'm glad you got my joke, Ava, because I was worried that no one was going to. Yes?
Was your question like, why is the solar day longer?
Yeah, in other words, we know that this is the correct answer now because we've worked it out together. But could you describe why? Like, could you put into words what's going on with those arrows in the diagram? What is the reason why the solar day is shorter than the sidereal day? How would I explain that simply, correctly, and elegantly? I've got a little stool so that my head won't block the board here.
I don't know how to say it elegantly, but it's going to be like pointing towards the sun before it reaches.
Wait, what is it? To say it elegantly,
Earth.
you have to know what it, not Earth. Earth doesn't point. Earth is a sphere. What is
Right.
point? What is the it? That's what matters here.
Will it be 12 p.m.? Like,
Once again, what is it?
The meridian.
Yes, the meridian. All right, now put it together. Say it better now.
all right, so the meridian would be pointing at the sun before it reaches the 360-degree rotation.
That's right. And to clean this up even more, we'll not just say everyone on Earth has a meridian. We're following a local observer. But you actually impressed me, guys. I didn't expect you to get that far. That's pretty good. This is because a local observer's meridian will point back to the sun before completing a full 360-degree spin. That's probably the best way to say that. So the arrow was the meridian. Okay, these are some tough questions today. There's no two ways about it. I'm just going to give you a second to finish this here. Students, can I erase? May I erase?
No, not yet.
All right, okay, that's fine. Hey, Joel, just a heads up, if you missed some of today's lecture, this was some stuff we didn't cover in 1020. So my lecture today got a little botched, but it's still something you should go back and check out at some point. You did not get stuff on the moon in sidereal time
Nope.
in your 1020 class.
Yeah, I have another class 11:30, so I have to go to that, and then I forgot that about the homework and lab stuff after. So
That's fine. Just take some time to go back and watch that hour-and-a-half lecture, flawed though it may be.
I will.
Whoever said, was that Nicole who said no? Nicole, let me know when
Yeah,
you're done.
I'm all set now.
Okay, you're good now? Cool.
Yeah.
All right, I'm erasing.
Thank you.
Hey, Nicole, while you're at it, do you want to read me the next question?
Sure,
Yes.
1 second.
S141?
Okay, so 41 is answer each of the following of your latitude. Where's north or south? Where's the north or south celestial pole on your sky?
Okay, wait, hold on.
Is part A.
Yeah. So let's start. So what's the title? Is the title, that's what I remember the title being, Fundamentals of the Local Sky?
Yeah.
And we have to answer them for our latitude, which is what?
It's where's your north or south celestial pole on your sky?
Nicole, what I meant is, what is the latitude of Rhode Island?
Oh, that's it's 42
degrees north.
Yeah.
Okay. And A asks what, Nicole?
It asks where's the north or south celestial pole on your sky?
What are we worried about for Rhode Island? The north celestial pole or the south celestial pole?
The north.
Good. So we have to find where is the north celestial pole in our local sky. Okay. Students, Nicole and students, anyone at all, what's the answer? I gave this answer to you on Monday.
Oh, I got it. So north.
Wouldn't it be 42 degrees north?
Yeah, so I want to be clear about this. You've got to use the horizon system. That means I want an altitude and I want an azimuth. I'm not saying you're wrong. I'm just saying I want to clearly know what's my altitude and what's my azimuth.
Your altitude would be 42 degrees and your azimuth would be 0 degrees north.
Excellent. Excellent. The altitude of Polaris is equal to your latitude, and the direction of the North Star is north, whose azimuth is 0 degrees. Nicely done. Who was that, by the way?
Morgan.
Oh, Morgan. Okay, I'm still learning everyone's the timbre of your voice there.
Yeah, I don't have a video, so you also can't see me because I know you have us. Yeah.
I see. That's okay. I don't mind. I like it when the trolls participate too. Participation helps the world go round here. Okay, Nicole, what's part B say?
Part B is describe the meridian in your sky, specifying at least 3 distinct points along it, such as the points at which it meets your horizon and its highest points.
Okay, you guys remember how this works. We need an altitude and we need an azimuth, and we have 3 points: the rise, the reach, and the set. I can give you some hints, or does anyone, you know, I don't like the, that's fine, I guess. Rise, reach, and set. Altitude and azimuth. Today we talked about what the meridian is. You know what? I think you guys want some help here. Let's get a picture. Here we go. The rise, the reach, and the set. Who can do it? I want an altitude and an azimuth for those 3 points. Start north.
Didn't we answer this on Monday?
Maybe we did. So what's the answer, Bella?
So I'm gonna say rise is 0 degrees, and then
Oh, wait. Bella. The rise requires 2 coordinates, an altitude and an azimuth. If you say 0 degrees.
I meant altitude 0 degrees.
Well, what's the azimuth then?
The azimuth is 90 degrees. East, due east? No.
Sorry?
Is it 42 degrees?
No.
No? Okay.
48.
Jesus. What's the definition of azimuth? No one knows what azimuth. What's the azimuth of this point right here?
Zero.
That's right. It's north.
Oh yeah. Sorry.
That's okay. And that's, of course, due north. What about the reach?
That would be 42 degrees,
Nope.
wouldn't it? No. Okay.
90?
Which coordinate are you giving me?
I was given the alternate. Oh.
Hold on, guys. You're a little unclear to me. Give me the altitude first.
Wait, for which coordinate? North, south, east, west?
That answer doesn't make sense. Azimuth is north, south, east, west. I'm asking you for the altitude of the reach.
Would it be 90 degrees, the altitude for
Correct. Who said that?
Matt?
That's correct, Matt, because you're 90 degrees above the horizon.
Mhm.
Nice. Matt, can you tell me what the azimuth would be?
Would it
Azimuth
still
means-
be 0?
Not exactly. Azimuth means what is the closest point on the horizon to this dot? What's the closest point along the horizon to the blue dot?
Undefined.
Who did that? Who said that?
Joel.
Yes. Who was that?
Joel.
Joel can see that it's equidistant from the
It's
horizon.
just like the North Pole.
Well, that's like with longitude in the North Pole, yeah.
Yeah,
Okay, so,
because it's at the top of the sphere.
yeah. So we'll just put a dash, it's undefined, but we can put over here, it's at the zenith. That's not really necessary because, of course, 90 degrees altitude is at the zenith, but whatever. How about the set point?
Is it 0 degrees again?
Which one?
Altitude?
Good, because it's on the horizon. What's the azimuth?
South?
South, what's the technical azimuth of south?
180.
Good. You guys are getting this, that's good. And that's, of course, due south. Due north, zenith, due south. 0, 0, 90, 0, 180. I'm going to erase. I'm going to erase now. Nicole, what's part C?
Sorry, I think I was on mute when I said that.
Oh, you were.
Describe the celestial equator in your sky, specifying at least 3 distinct points along it.
Okay.
0 degrees altitude, and the azimuth is 90 east.
Very good. In other words, excuse me, I'm sneezing a lot today. This is the rise, this is the reach, and this is the set. And Bella just gave us this one here. 0 degrees altitude in a direction east. That's the same thing as due east. What about the reach? Very good, Kevin. Kevin says the reach should be 48 degrees and the azimuth is 180 degrees or south. Remember that Kevin probably knows this angle is 48 degrees because he remembers the alpha, beta, gamma, delta game from our class last time. Alpha, beta, gamma, and delta. Beta was our latitude, so alpha is 90 minus our latitude, which is 48. Nicely done, Kevin. How about the last one, the set point? This might be a test question. Just saying.
0 degrees altitude.
Uh-huh.
270 degrees azimuth, or due west.
Cool. Good. Good, Kevin. Good, Joel. Due west. Well, they don't call it home fun, right? They call it homework. That's how it goes. I need to erase. Adam, let me know when you're good. All right, I'm erasing.
I need another second.
Sure.
My internet shut down.
Oh, that's okay. Just let me know when you're good, whoever you are. I know, I live in fear that one day National Grid is going to come and like snip the wires during my lecture. That's only happened once since all this crap has started, but I have no idea what I'm going to do if that happens.
I'm all set.
Okay, cool. Nicole, could you read us D?
D is, does the sun ever appear on your zenith? If so, when? If not, why?
So this could be slightly tricky. Will the sun ever appear at your zenith? Let me show you a picture that I showed you today, showing you the path of the sun in our local sky. I wish I had spent more time on this. Honestly, I really should have. This picture is like a little nicer in terms of graphic design, but it's kind of twisted at an angle here. This picture is less skillful graphic design-wise, but in a way, I think it's a cleaner picture because you have north on the right the way we're used to it. This would show you the path of the sun 3 different days from a latitude similar to Rhode Island's. If there was ever a day where the sun could reach our zenith, what day would that be?
Summer solstice.
Right. So one thing we could start by doing is figuring out how far up could the sun get on the summer solstice. Now on the spring equinox, the sun is on the celestial equator, right? So on the spring equinox at noon, this is where the sun is. What's this angle again, Kevin? Kevin knows this angle.
Is that 48 degrees?
That's 48 degrees, good. Now, how many degrees above the celestial equator can the sun get? What's this angle here?
42.
Right. Pardon?
23.5.
Right. The sun can go up to 23.5 above the celestial equator and 23.5 degrees below the celestial equator. So what do you get when you add 48 plus 23.5?
$71.5.
So what's the answer to the question? What is the question?
Sun at
No.
zenith.
Okay, sorry, what's the answer then?
70.5 degrees.
Not really. The question was, will the sun ever reach your zenith in the Rhode Island local sky?
Answer is no.
All right, why not, Morgan?
If you go back to the graph, it's because the highest point is 71.5 and the zenith is past 71.5.
The zenith is at 90. Good.
Yeah.
So let's write down no. The sun will never reach the zenith in the Rhode Island local sky, but only reach a max altitude of, let's remember how we got there, 48 degrees plus 23.5 degrees equals 71.5 degrees at noon on the summer solstice. That's the best possible answer I could think to give. Hey, I'm going to ask you guys a challenge question because I think it's important. Morgan, I'm going to pick on you for a second.
All right.
Morgan, I'll even give you a hint. What do you think is the maximum latitude you can go to on Earth, the most northerly latitude, and still have the sun appear at your zenith at some point throughout the year? Clearly, if you're on the equator, the sun will cross your zenith from time to time, like on the spring equinox or the fall equinox. How far north can I go on Earth and still have the sun appear at my zenith? Clearly, Rhode Island is too far north, so you've got to have to be somewhere below Rhode Island. This is 0 degrees latitude. How far up can I go? Anyone who thinks they can scoop Morgan is welcome to.
I'd say 30 degrees.
No.
66.5.
No.
23.5.
What's that?
23.5.
Who said that?
Noah.
I'm sorry, who was that?
Noah.
Noah, yeah. Noah, explain that to me.
Well, if the sun can only go 23.5 degrees north or south of the, I don't know what it's called, the equator.
The celestial equator, but yeah.
Yeah, then it can only be directly overhead.
At
like,
at a ring of 23.5, right? And
right.
the sun on that day is 23.5 degrees above the celestial equator. So the maximum, I need to draw this clearer. The maximum latitude on Earth would also be 23.5 degrees. Is this angle here is 23.5 degrees, right? There's a special name for that, Noah. Do you know what that latitude is called? 23.5 degrees north?
Is it the Tropic of Cancer?
Very good. This is what defines the tropics, where the sun can reach the zenith. 23.5 north is the Tropic of Cancer. 23.5 south is the Tropic of Capricorn. What makes the tropics is this is a wedge where the sun can actually reach your zenith. It can get directly overhead. We're too far north of the Tropic of Cancer for the sun to ever reach our zenith. Okay, the next question is even harder than that one. Nicole, let's read. Hold on. Can I erase this?
No, I'm not done copying.
All right, Andrew, you let me know when you're good.
What is that now on the summer? Oh.
At noon on the summer solstice. I need to start writing larger. Sorry about that. The sun, you know, it's hard. I have kind of a small board compared to a big classroom, so it's tough. All of a sudden.
Just take your time writing.
Well, if I do that, we'll be here for 3 hours, and then you guys will really want to kill me.
Yeah, but you said when you rush your writing, it gets sloppier.
No, I know. I know.
So I got half a second longer.
Okay, Joel. Actually, you're not wrong. You're not wrong. Okay, I'm going to erase now, Andrew. You good?
Yeah, I'm all set. Thank you.
I have sloppy handwriting too, Brendan. You've seen it.
Let's try E. Nicole, you can read that when you're ready.
E is what range of declinations make a star circumpolar in your sky?
Okay, what are circumpolar stars? Who remembers what a circumpolar star is? It's a circumpolar star.
They're stars that never rise or set.
Right. So, are all of these stars circumpolar?
No.
Which ones are circumpolar?
The inner ring.
What, inner to what?
Polaris, isn't it?
Polaris is circumpolar. There's Polaris, that's circumpolar, okay.
The orange, the second orange line, like, yeah, below that one. Yeah, that one. Everything above that.
Okay, yeah, kind of, you're right. I suppose if a star was like here,
yeah,
that would be circumpolar too, right? Right. But all these are not circumpolar because they set. Oops.
So is it if it's orange, it's circumpolar, but if it's blue, it's not?
No. Circumpolar stars are those stars which orbit close enough to Polaris where they make a complete circle in the sky that does not go below the horizon. So all of the circles in red are circumpolar because they don't go below the horizon. But once you go like this, you're not circumpolar anymore because then you set below the horizon. Does that make more sense?
Yeah, it does.
Okay. Now let's look at some other parts of this question. We have to understand the question. What are the range of declinations? First of all, what does range mean? What do they mean by range?
From this point to this point?
Correct, Andrew. From some minimum value to some maximum value. So this is what our answer needs to look like. I'm going to use the letter delta for declinations. The declinations should be greater than or equal to some minimum value, less than or equal to some maximum value. And we've got to figure out what those values are. We also need to remember what declinations are. And I'm guessing that a few of you forgot. If I ask this class right now, pop quiz, what does declination mean? I bet 70% of you would fail it. Let's see if there's anyone out there that does know. What's declination? Maybe 100% of you would fail that quiz, actually.
Direction.
No. Well, you need to be more specific than that. Declination.
Angular direction.
That's not enough. That's too vague. Why don't you just read it out of your notebooks? I give up.
Check the chat, Brendan.
Huh?
Check the chat. Brendan answered it.
Oh, okay.
Or gave an answer.
Brendan, okay. Angular. Brendan, I don't like the term angular distance. A distance is a length measured in kilometers or meters. Angles are angles. Let's say it's the angle north or, and by the way, we don't use north or south either.
Degrees are positive or negative from celestial equator.
That's right. We use plus and minus. Okay, so what's the declination? Actually, what's the declination of the red ring here? What's the declination of this ring?
48 degrees.
No, that's altitude.
Would it be positive 12?
No.
Isn't it 0?
Yeah. Your celestial equator is the 0 point of declination. So this, the declination of this point is 0 degrees. What's the declination of the north celestial pole? Oops. What's the declination of your north celestial pole?
Positive 38 degrees.
False. Declination are your degrees plus or minus from the celestial equator.
'90.
Positive 90. Okay, first thing I'm going to ask you is this. What are the total range of declinations that a star can have, period, on the celestial sphere? If you can't answer that question, you're not going to be able to answer this question. What is the total range of declinations a star may have on the celestial sphere? For instance, a declination of 2,683,000 is not valid. That's not within the range. What are the total range of declinations on the celestial sphere?
Between 0 and 180?
False.
Negative 90 and 90.
Very good. Who said that?
Noah.
Noah, you understand. The celestial equator is in the middle, and that's 0. It goes from -90 to +90. Very good. Okay, Noah, let me show you a picture from your book here, a picture that I think is really beautiful. It's a picture of circumpolar stars as seen at the Grand Arches National Monument in Moab, Utah. And this is a beautiful photo. Someone who took this was very clever. They set up their camera at night so that Polaris appeared in the middle of the arch, and they took a time-lapse photograph showing stars orbiting the sky. You can see there's some circumpolar stars in here. There's Polaris. Is Polaris circumpolar, Noah?
I don't know.
Yeah.
Yeah, Polaris doesn't rise or set. It's always in your sky. What's the declination of Polaris?
40.
That's its altitude. We're
Positive
on
90.
the horizon in the equatorial system. What is the declination of Polaris?
Positive 90.
Good. Can there be any star with a greater declination than positive 90?
No.
Then we've found our maximum. The maximum circumpolar star is Polaris. The real question is, what is the last circumpolar star? What's the minimum declination? So let's start here. Observe that this star here, that star is the last circumpolar star in your sky. What is this star doing that no other star is doing? What makes this the last circumpolar star?
The fact that it doesn't rise or set.
Okay, but none of the ones inside that circle rise or set. Why is this the very last one?
It doesn't dip below the, that's like right on the edge before it dips below the horizon.
The horizon in which direction? Which direction is this?
Down. North.
Right, because that's where the North Star is. So that's the star that grazes your northern horizon. In other words, share screen. The circumpolar stars are all orbiting around Polaris. Let me do circumpolar in purple here. So this is a circumpolar star, that's a circumpolar star, that's a circumpolar star. The last circumpolar star is that star which just barely grazes your northern horizon. If only I knew the declination of my northern horizon, I would know what the declination of the last circumpolar star is. Let's work this out. So the equator is 0 degrees dec. The north celestial pole is positive 90 degrees dec. What's the declination of your zenith? The zenith actually has a declination. What's the declination of the zenith?
45.
False. Not for Rhode Island, it's not. Not 45.
48 degrees.
False. This
42?
angle, yeah, that's the beta angle. That's positive 42. What's the declination of your southern horizon?
Minus 42.
No, that's the alpha angle.
Minus 48.
Minus 48. Okay. This is tricky stuff. Now here's your hint. If you want to know,
how?
Because the altitude of the celestial equator is 48 degrees. It makes a 48-degree angle. We know that the angle from the equator to the zenith is your latitude, which is 42 degrees. That's a 90-degree angle, so the angle here to here is 48. You've got to review the alpha, beta, gamma, delta game.
Oh.
Then we measured declination from the celestial equator. It's minus 48 down from the celestial equator. Okay, here's your hint. The celestial equator extends down here through the part of the sky that you cannot see. The declination of your northern horizon are the degrees above the celestial equator. What's the declination of your northern horizon?
48.
Sorry?
48.
Whoever's saying that is so quiet, I can barely hear you.
48.
Positive 48. We know that this angle is 42 degrees. So that angle is positive 48 degrees. Nice. That was not easy. Nicole, read part F.
Part F is, what is the range of declinations of stars that you can never see in your sky?
Now, I refer to these stars as anti-circumpolar stars. I don't know if other astronomers call them anti-circumpolar, but I do. In other words, the circumpolar stars are the purple stars which never set below the horizon. There are some stars that are below our horizon that never rise. They kind of circle the south celestial pole. Actually, it's kind of sad. There are a number of really cool objects that we can never see at any time of the year from the Rhode Island local sky. In particular, the large and small Magellanic Clouds are beautiful galaxies that you can see with the naked eye, only from the southern hemisphere. I've always wanted to be able to see them, but I haven't been to Argentina before. Anyways, what do you guys suspect? Do you want to take a guess? What do you think the range of anti-circumpolar stars are?
Negative 48, negative 50, or negative 90?
That's right. The minimum is minus 90. And the maximum is minus 48. Those are tricky problems. You have to think pretty hard about that. You have to know what every single term means to answer this question. You got to really know. Okay, 2 down, 3 to go. Can I erase? Okay, Cam, that's good. Jake, you down to read a question?
With
Yeah,
this
47.
recorded, I have to go soon.
I'm sorry. Okay, hold on, wait. Let me deal with this one at a time. Who says they have to go soon? Is that you, Andrew?
Yes.
Andrew, this is an office hours that takes the full 2 hours. So if you have to go soon, fine, but here's what you got to do. I'll have this video posted in a couple of hours. You need to come back, watch the rest of it, finish your homework, and submit it. Can you handle that for me?
Yeah, I can handle it.
You've got tomorrow and Friday and at very worst Saturday. But Sunday I grade and then I cut it off.
All right.
Hey, by the way, some people are having trouble with those consequences. I keep getting emails from people saying, oh, I'm sorry, I knew there was a deadline and I had some stuff going on. Some of you actually have legitimate hard stuff going on, like family members getting sick and work. And so I don't want to belittle that stuff. The problem is I'm the conductor of this crazy ass choo-choo train with 160 people on it. And I have to kind of keep moving from station to station. I don't have a choice. I have to cut things off on Sunday. So Andrew, you've got a little bit of wiggle room, but get it in by Sunday. You can make it.
All
Only,
right.
it's going to take
with
you
this recording,
Yes, this is being recorded. Okay.
will it be up by today?
Yep. It'll take an hour to render it. We're going to finish a little after 3 o'clock. It'll take an hour to render it, another half an hour to get it on YouTube. I estimate by 4:30 it'll be up.
All right, I'll get that done.
Thanks, buddy. Okay.
No
The rest of you, let's go on to the next problem. Jake, did you say you were down to read?
Yeah, 47, right?
Yeah.
All right. Lost at Sea 1. During a vacation, you decide to take a solo boat trip. While contemplating the universe, you lose track of your location. Fortunately, you have some astronomical tables and instruments, as well as a UT clock. You thereby put together the following description of your situation.
It is the March equinox. The sun is on your meridian at altitude 75 degrees in the south. The UT clock reads 2200 hours, I guess. What is your latitude? How do you know?
So the latitude, you guys can answer that. We'll answer it together, of course, but the latitude you've been prepped for. I did not get to universal time today because I spent too much time on the moon. So I'm really unhappy with how I prosecuted the lecture today, but whatever, sometimes this stuff happens. Why don't we start by drawing a picture of our givens? It's the spring equinox. The sun is 75 degrees south on the meridian. The universal time clock, let's write this down. This is the mean solar time at the prime meridian.
I have a question.
Yeah.
I just lost internet connection for a good 10 minutes, and the last thing I wrote down, we were talking about the range of declinations.
Declinations.
And my internet cut off, and I lost Zoom class, so that's where I last was.
So you missed two small parts, and there's two different ways to go about this. One is wait for a couple hours until the lecture is posted online, watch the little bits, fill in the blanks, and you're done. Another option is that Cam has been taking some snapshots, haven't you, Cam? So if you wanted to save that poor soul a little bit of time, if you have a snapshot of E and F, you could send it to the group chat, and that might help out quite a bit. Unfortunately, you will have lost the meaning and the understanding. Getting the answers, hell, I can give you the answers in 10 seconds, but going through the torture process is how you learn. So you may want to think about going back and watching that for your own sake.
Okay, thank you.
So Cam will attempt to send. Do you know how to do that, Cam?
I think so.
You
I
go
have
to
Zoom on my phone.
That's fine. I can always just go back in the video when you upload it later. That's okay too.
Okay, Kelly, that's probably the simplest way to do it. Cam,
Yeah.
I didn't realize you were watching on your phone. I thought you might be watching on a computer.
I am watching on a computer, but I have Zoom on my phone as well. I'm using Zoom on my PC right now. That's
right.
what I'm saying.
How would you do this? If you want, you can
I don't
just
know if I can.
Here, you want to do it simple. Email me the picture to bbritton@ccri.edu, and then I'll share it with the class.
You want me to email it to you?
Yeah, just do that. That's simplest. Just
Okay.
email that, because you can hit the button and send an email directly to bbritton@ccri.edu.
I'll try.
All right. All right. To do a lost at sea problem, we're going to have to write these givens down, and then we're going to make a diagram. Everyone take a moment to write this stuff down, because I'm going to need to erase it.
Excuse me?
Yeah, sure.
What is it? What is that M word next to the 22.00?
Mean.
Oh, okay. Thanks.
Like mean old junkyard dog, okay? Mean solar time at the prime meridian. Don't worry, I'll explain it again in a minute. Can I erase? All right, everyone draw the following picture with me. Make a line, leave some room somewhere on your page. Make it 12 centimeters. Mark the midpoint halfway through. Mark your zenith, and we're going to draw in a dome. Let's put a boat in the center of the ocean. okay? And let's have a sailboat that has its mast pointed up towards the zenith. This is the zenith. There's your sailboat, okay? You want to make it fancy, put some waves in. Okay? And I always like to put north on the right-hand side, south on the left-hand side. Class, tell me where to put the sun. Where does the sun go in this diagram?
On the south.
Whereabouts? This entire portion of the sky is the southern sky. Whereabouts in the southern sky should I put the sun?
A little above that dot that you made.
That dot?
A little above it, I think.
Yeah. Let's see here. I can use my protractor, right?
Halfway between that dot and the zenith.
I put this over the dot. It looks 75 is actually pretty high up. 15 degrees, right? Okay, let's see. 15 degrees goes into 90 4 times, right? So if I break this into 4 parts.
What? No, it's 6. Goes in 6 times.
Sorry. Thanks, I was just testing you. That's where the sun should be, right?
Yeah.
It should actually be pretty high up. Why did they bother telling me it was the spring equinox? Why would that be important?
It's a place, isn't it?
It's different than that.
4 things at once, I'd like.
It's 4 things at once. That's what this is all about. It's about the 4 things at once. And it's about this picture here too. The day is the spring equinox. But by knowing that the day is the spring equinox, that should tell us where the spring equinox is on our local sky. Where's the spring equinox? Where is the spring equinox at noon on the spring equinox? That's what I'm trying to ask you.
On the celestial equator.
Whereabouts? This is a celestial equator. It's a big old ring here. Can you be more specific? Whereabouts? Yes, you are correct. That's where we're going. You got the right idea. Whereabouts is the sun on March 21st?
At 0 degrees.
Well, all of this is 0 degrees declination. Look, the spring equinox is always on the celestial equator. The question is, where is the sun? Someone use their drawing tool and point to where the sun's going to be on March 21st. You guys can draw on this. It's not just me. Where will the sun be on March 21st?
At the peak.
What the hell does that mean?
At the vernal equinox?
Yeah. Yeah. That's where the sun's going to be on March 21st, right there. On the spring equinox, the sun is on the spring equinox. So where's the spring equinox?
Where the sun is?
Okay. Where's the celestial equator?
Also where the sun is,
Good.
because it's the spring equinox.
So this is not only the spring equinox, it's also the celestial equator. That's the point. That's why they told you it was the spring equinox, so that you would know that the sun was stuck to the celestial equator. Okay, so what's our latitude?
$75 south.
False. Consult the alpha, beta, gamma, delta game. Here's a hint. If this is the celestial equator, the north celestial pole, or one of the poles anyways, should be up here, right?
Minus 75 degrees.
There's no such thing as a latitude of minus 75 degrees.
48 degrees.
False.
23.5.
False.
Positive 48 degrees.
False.
15 degrees.
Who said that?
Noah.
Noah, that's ambiguous. 15 degrees north or 15 degrees south?
I believe north, but I don't.
Out.
First of all, Noah recognizes that the latitude is the angle between the celestial equator and your zenith. The latitude is 90 degrees minus 75 degrees is 15 degrees. He correctly suspects that it's north. The reason why, Noah, is because the sun is in the south when it's on the celestial equator. Let's just look at a picture here of northern hemisphere versus southern hemisphere. In our northern hemisphere view, unfortunately, this is reversed from our picture. If you're in the northern hemisphere, the sun travels through your southern sky. If you're in the southern hemisphere, that's the best I got. In the southern hemisphere, the south celestial pole is in your sky, and the celestial equator goes through your northern sky. Basically, it's like this. Sun is in the south, you are in the north. Sun is in the north, you are in the south. That's why you're 15 degrees north. B, our longitude. You can get your longitude by figuring out how many hours east or west of the prime meridian you are. And here's where I failed you a tiny bit. I didn't get to kind of an important note in our lecture. It wasn't a very long-winded one. It was just saying, you guys may have heard of time zones before. Obviously, the sun is constantly rising and setting at different locations on Earth, right? So if you consider apparent solar time, the sun is supposed to be at your meridian at noon. When the sun is at the meridian of an observer in Washington, D.C., it will not be at the meridian of a person in Los Angeles. In the golden oldie days, in the 1600s, that didn't matter because most people didn't really leave their little towns, and if they did, they took a horse and buggy to some neighboring town where the times were appropriately the same. However, in the 19th century, when people started developing the transcontinental railroad, people could suddenly cross crazy numbers of longitudes in a very short period of time. In a day or so, you might go from the east coast of the U.S. to the central United States. And as they crossed so many local time zones, they had to have these complicated train schedules, which had the time in Boston, the time in Pennsylvania, the time in Ohio. And it got so confusing that the train companies actually introduced standard time, and they broke the United States into 4 time zones. People around the world later realized the usefulness of this, and they decided to break the entire Earth into a set of time zones. Each time zone spans approximately 15 degrees of longitude, or roughly 1 hour of time. So today, when we keep universal time is the mean solar time at the prime meridian at Greenwich, England. That's sometimes called GMT, Greenwich Mean Time. And then everybody is offset from Greenwich Mean Time by some number of hours that depends upon their longitude. You can calculate your longitude if you know the difference between your local solar time and you know the time in Greenwich, England. The time in Greenwich, England is 2200 hours. But class, what do you suspect is the local time for this sailboat here? What would the local time be if you were in the sailboat? With
1200 hours.
Yeah, how did you know it was 1200 hours, Joel?
This is spring equinox.
No, not because of the spring equinox, because of a different reason. It's because of where the sun is in your local sky.
Yeah, that's what I said.
Well,
I just said it backwards, and in not so many words.
how do we define noon? What is noon supposed to be? We define time by the sun. Where do you want the sun to be at noon?
The highest point.
On your meridian. And therefore, the local time here must be 1200 hours, not because it's the spring equinox, but because the sun is on your meridian. So how many hours off are we from England? 2200 hours minus 1200 hours equals what?
Ten.
So how many lines of longitude would that correspond to? How do we convert from hours to degrees on Earth?
Multiply by 15.
Times 15 degrees per hour.
So that'd be 150 degrees west.
Yeah, that's the tricky part. We have to do east or west. How do you know it's west?
Because we're 10 hours behind. And
Yeah.
you have to go west. You have to go to the left to get there.
Yeah.
I don't know how to eloquently say that.
I know, it's very difficult. Joel has some practical experience here because he's been in the military and he's traveled the world a bit. And this is where it can really help you to have those experiences. For instance, Joel, here's how I do it. I know that my friends in England, when I'm lucky enough to have friends in England, they're later than me, right? Like if it's noon o'clock here, it's going to be like 5 p.m. in England, right? I know that Rhode Island is west of England, and I know that Rhode Island is earlier. So in my mind, Joel, I kind of do it the same way. I say, if you're earlier than Greenwich, you're west. If you're later than Greenwich, you're east. Clearly, noon o'clock is earlier than 2200 o'clock, right? So we are also west. That can be tricky. So the answer is 150 degrees west. And there's a little part C, which we can do quickly. What's the question for part C, Jake?
Part C. Consult a map. Based on your position, where is the nearest land? Which way would you sail to reach it?
I'm going to help you out through this one, guys. Let me get my focus adjusted here. I think if I focus like to 30. Okay. So let's see if you guys can see this here. So here's 90 degrees west. let's go to 150 degrees west. There's 150. And look, this is 15 degrees north. So we're located right there at that dot. Where's the nearest land?
Hawaii.
Hawaii.
Which direction do we have to sail?
Left.
Northwest.
Northwest. Very good. Nicely done. Now you know how to save yourself if you're lost at sea, provided your clock keeps universal time.
I didn't join the Navy, so I don't have to worry about that.
Well, you never know, man. One day you could be sailing around the harbor. So the answer
Fat chance at that. I don't go in the water.
sail northwest to Hawaii. I'm just giving a moment for everyone to catch up to me here.
Hey, Brendan.
Yeah.
So we use Zulu time in the military.
Right.
Is that the same as UTC?
Greenwich Mean Time. Yep. For some reason, the military they call it Zulu time, but it's the same thing as universal time is Zulu time.
Okay.
By the way, there are other curious ideas about how we could keep universal time too. The Swatch Company, a few years back, tried to invent this type of universal time called Internet Beat Time, where you didn't use hours and minutes and seconds, but you used beats as the interval of time, and everyone would keep the same time everywhere in the world, no matter where they are. It's totally wacky and weird. If you want to read more about it, just go to Wikipedia if you're like a watch enthusiast, and you should definitely read about Swatch Beat Time or whatever it is.
So they wanted to say that
Swatch Internet
noon,
time.
noon in England would be noon here, even though
Wait.
it would be 2 a.m.
Yeah, but they gave up on AM and PM and all this stuff. In 1988, instead of hours and minutes, the mean solar day is divided up into 1,000 parts called dot beats. Each dot beat is equal to 1 decimal minute in the French Revolutionary Decimal Time and lasts 1 minute and 26.4 seconds. And they don't even bother with time zones. They just keep beat mean time or whatever it is. And everyone, the idea is that the internet was going to revolutionize time, and it wouldn't matter if basically they were trying to abandon the sun as a timekeeping system. It's totally insane, but very interesting.
Well, hell, nobody respects the French military. Why do we don't respect the French terminology and stuff?
Well, I'm not going to go there because I don't want to step my foot in it here, but all I know is
dang Swiss.
It's a cool idea. That's all it is. It's a cool idea.
Yeah, it's interesting.
But nobody, of course, liked it because it turns out people like keeping time by the sun. Our biological clocks are innately tuned to the motions of the sun. In any case, let me erase and we'll move on to our fourth question, 51. This one's going to require a little explanation. 51 is the easiest question we have to do today, but I need to teach you a couple of formulas to do it. Okay. S151 has to do with the difference between a planet's sidereal period and a planet's synodic period. Let's let P Sid be the sidereal period of a planet in years, where the sidereal period is the true 360-degree orbit of a planet like Mars or Jupiter or something like that. Let P sin, S-Y-N, represent something called the synodic period. It's a different kind of planetary period. It's the time for a planet to orbit the sky as seen from an observer on Earth. Let me explain why there should be a difference. By the way, sidereal in Latin means stars. Synodic in Latin means a meeting point. Cam sent the picture to my email. Whoever that was who got disconnected, could you remind me to send you that picture at the end there?
It was Kelly. And yes, thank you.
Okay, Kelly, don't forget to remind me. Before I show you the two formulas you need for this problem, I want to explain why there's a difference between a sidereal and a synodic period. The book explains this pretty eloquently. I found a nice picture here. I'm going to tell you guys that the orbital period of Mars, its sidereal period, is about 2 years to go around the sun. So let's imagine what happens during a 2-year period as we orbit the sun. As you know, Earth takes 1 year to go around the sun. And that means in 1 year, Mars doesn't complete a full orbit. It kind of goes to about here in its orbit. Another half a year later, Earth catches back up to Mars and they have an alignment. This alignment is sometimes called a conjunction. Now, Mars may not have gone all the way around the sun, but if you're an observer standing on Earth, it kind of looks like Mars has come back to the same place in the sky because Mars is now on the opposite side of Earth from the sun. In other words, Mars kind of has the same position that the full moon does. And just like the full moon will rise at 6 p.m., set at 6 a.m., and cross your meridian at midnight, in this configuration and in this configuration, Mars will cross your meridian at midnight. So if you're standing on Earth, it looks like Mars is back to the same place in the sky. It's completed one synodic period, but it has not completed a sidereal period, a true 360-degree orbit. I can explain that a little better next time as well. Normally, the synodic period is what you observe from Earth. And normally, the sidereal period is what you want to find or what you want to calculate. So most people are interested in the true periods of the planets around the sun, but they have to start by observing the synodic period. Luckily, there are formulas to calculate these two. I'm going to erase this here. The formulas depend upon whether you are an inner planet or an outer planet with respect to Earth. For inner planets like Mercury or Venus, the sidereal period is the synodic period divided by the synodic period plus 1 year. For outer planets like Mars, Jupiter, and Saturn, the sidereal period is the synodic period divided by the synodic period minus 1 year. This is the thing that I screwed up on today. I ran out of time and I didn't get to introduce these two formulas. Luckily, the formulas are not overly complicated. They're pretty easy to put into your calculator, and I'm going to show you how to do it. Everyone take a minute to write that down. You can write it down right inside your homework if you want. And then we're going to solve 3 simple problems using these 2 formulas. Oh, make a note to self. All times must be in years. Okay. Okay, I want to erase and start the problem.
Wait, hold on. Sorry.
Sure, that's fine. Are we good?
Yeah.
Hey, Joel, can you read this one for me? S151.
Orbital and synodic periods. Use each object's given synodic period to find its actual orbital period. Part A is Saturn, and the synodic period is 378.1 days.
Is Saturn an inner planet or an outer planet?
Outer.
So we need to use the second formula. The sidereal period is the synodic period divided by the synodic period minus 1 year. Days are not allowed. What are you going to do about that, Noah?
You have to make it into a fraction to be like years.
Yeah, that's dimensional analysis. Can you walk me through that?
Yeah, so it would be 378.1 days.
I'll just use a little d for days. Yep. Now what?
Times 365.
Whoa. Noah, slow your roll. That's not how we do dimensional analysis. We have we have a procedure here, right?
Right. Oh, it's times 1 year over.
No.
It's a divide bar.
Bella understands me. We make a division bar.
Then
Noah,
go
ahead, Bella. Show him how it's done.
So then you put days on the bottom and then year on top.
Okay, let's pause here for a second. Noah, you need to understand why this is an important method, even for you. You need to get in the habit of putting your units in first and your numbers in last. Because you're very quickly going to go into a part of this class where we deal with some wacky abstract shit that you're not familiar with. You might already have a vague sense of how many days are in a year and all that stuff. But once you start working with electron volts, things are going to get much messier. So you need to develop good habits. Joel knows. So notice what Bella did. Bella put her units in first. Now, Bella, we put the numbers in second. So Bella, where do the numbers go?
So it's 365 on the bottom.
Yep.
And then 1 on top.
Actually, I have an issue with that, Bella. Normally, 1 year's 365 days is a perfectly good conversion factor to 3 significant figures. But how many sig figures did they give us in the problem?
It gave us 4.
And that means your conversion factor is going to pollute your answer. It turns out that synodic and sidereal periods, the precision really matters. So how can we get this up a few notches of precision? Do you know the number of days in a year to greater than 365?
No.
0.25.
It's 365 and a quarter, yeah. 365.25.
Because of leap year. You
Pretty
set a
much,
day
yeah.
every 4 years too. For the
Hey Joel,
quarter
do you
day
mean
every year.
Joel, do you mean a sidereal year or a or a tropical year?
Oh, come on, just stop messing with my
They're
head.
different by 20 minutes. I shouldn't do that to you. Okay, 365.25 is fine. What do you get, guys? Give me your answer to how many sig figs? Punch them up. Well, what do you got? Okay, Cam, but how do I round it? Juan, that doesn't look so right to me. Cam, what are you going to round your answer to?
To whole number?
No. What's your limiting precision? Maybe I need to say this slower and simpler.
Yeah,
Which
I'm a little
number
confused.
is your shittiest number?
Oh, 1?
Oh, that's a perfect year. That I see what the problem is. Okay, this is going to seem unfair, Cam, but 1 is not a measurement. 1 is the concept of a year. The concept of a year is the time it takes Earth to go around the sun. So it's a perfect 1, but unfortunately, there are not a perfect number of days in 1 year. There's a measurable number of days in a year. Does that make sense? So ignoring
so.
1, what's your crappiest number, Cam? Help him.
365.25.
False.
368.1.
378.
78.1.
How many sig figs does that number have?
How many?
4.
Okay, so round this to 4 significant figures.
Just delete the calculation.
You're wrong, Brendan.
What? I'm wrong?
Yeah.
In what way?
378.1 divided by 365.25.
Oh, you're right. Wow. I screwed up somehow. Thank you.
Yeah, I have the same one.
The 1 was right.
Juan, I apologize to you in front of the whole class.
Yes.
Okay. Nope, that's not 4 sig figs.
$1.035.
Yes. Units?
Years.
Years.
That's what we need to plug into our synodic period. So let's set it up. Our synodic period is 1.035 years. Divided by, open parentheses, 1.035 years minus 1. Let's practice using our parenthesis keys together. Okay, watch me. 1.035 divided by, open parentheses, 1.035 minus 1. We close the parentheses and then we hit equals. Oops. What did you get?
29.57, bunch of other numbers.
What are the units? 4 sig figs. That's why 29.57. Units.
Years.
Okay, let's see if we can do the other ones a little faster. That's part A.
Wait, it takes.
That's how long it takes Saturn to get around the sun. 30
Holy
years.
crap.
Exactly. This is why manned missions to planets at the outer solar system get more and more tricky, because you have to wait longer for them to. Well, actually, no, that's not true. The synodic period is only 1 year. So you line up with Saturn every year. It's a little, anyways, it's a little tricky. You have to have the right orbit and stuff.
All right, so part B.
All right, I'm erasing. Part B.
Is Mercury. And their synodic period is 115.9 days.
Noah, why don't you show me how it's done right this time? Help me convert that into years using my methods.
All right, so 115.9 days times the bar thing, yeah. Days on the bottom, years on top. 365.25 days on the bottom. And 1 year on top.
Excellent. Trust me, my friend, you will thank me for this. At some day, you will thank me for this. Okay, so punch them up and give me 4 sig figs. Oh, yeah, 4 sig figs. Come on, guys, this shouldn't take a very long time, right?
I got 0.317.
I want 4 sig figs. Good one. 4 sig figs, though. The zero's not a sig.
0.3173.
Units?
Years.
Now, this has to go into our formula for inner planets. The sidereal period is the synodic period over the synodic period plus 1 year. That's because Mercury is an inner planet. So we have 0.3173 years divided by parentheses. All that. Three, 713 divided by open parentheses 0.3713 plus 1 close parentheses.
You did it wrong, Brendan.
It's 1-7, not 7-1.
Oh,
It's 3173.
Thanks, guys. 0.3173 divided by open parentheses 0.3173 plus 1 close parentheses equals 0.2409 years. Okay. You know what? By fiat, by declaration of the king, I declare that part C is unnecessary. All you night students listening later, you're just responsible for 51A and B. That's because this homework is kind of intense, and I should have cut down on it a little bit, okay? Those two problems are enough to get you the flavor of the feeling. So that's going to be all for 51. I want to move on to the last problem. I don't think there's any objections to that, right? No, yeah. This is, I warned you guys, this is a pretty nasty homework, one of the harder ones. I'm going to erase all this.
Just a quick question. If we were to do the letter C, how would we know if the asteroid is in front or behind us in the solar system?
Very cool question. I honestly didn't expect anyone to give a shit. So the fact that you do give a shit makes me very happy. The reason how you would know is because you would be a science nerd like me and you would know where the asteroid belt is. Does anyone out there know where the asteroid belt is?
Right after Mars.
Exactly. So according to that, would we use the inner or the outer formula?
Outer.
Yeah. It doesn't matter if it's a planet or a comet or whatever. If it's inner the Earth ring, you use the inner planet formula. If it's outer Earth ring, since by far the great majority of the asteroid belt, asteroids are mostly, you can see it's not entirely true, but most likely your asteroid is somewhere between Mars and Jupiter. So we would have used the outer planet. There are a few weird Earth-crossing asteroids which come interior to the planet. That's a little bit more tricky, but they didn't have that in mind for you, okay? So hopefully that answers your question. Okay, 53A is going to be a problem about local sidereal time, which you learned at the end of class today. Actually, we'll just call 53, chapter S1. Local sidereal time, okay? And in part A, I'll actually be the reader here, because what the hell? It's 4 p.m. on the spring equinox. What is the local sidereal time? Let's draw a little cartoon picture of what's going on here. I'm going to make a quick and sort of cheap local sky diagram. It's always helpful to kind of draw a little two-dimensional local sky for these problems. Remember, in local sidereal time problems, we want to go east to west. This is your meridian up top. If it's 4 p.m., that's telling me something. It's telling me where the sun is in my local sky. Can you guys tell me where to put the sun in the local sky here? Where should I put the sun in my local sky?
In the west?
Whereabouts in the west? All of this is the west.
On the, well, it's the spring equinox.
Hold on, you don't need to even get there for a second. Just 4 p.m. 4 p.m. tells you the hour angle of the sun. Where should the sun be in your local sky at 4 p.m.?
Almost setting?
Yeah, somewhere over here, right?
Mm-hmm.
Four p.m. tells you the hour angle of the sun. It tells you that it's 4 hours post-meridian. Now, how is that supposed to tell me the local sidereal time? What is the definition of local sidereal time?
Wasn't it 23 hours and 56 minutes?
That's the sidereal day.
Oh,
it's,
okay.
It's related, but it's not the definition of local sidereal time.
Is it the hour angle of spring equinox?
Correct. So in other words, if you knew where the spring equinox was in the sky here, you would know the local sidereal time. So where is the spring equinox on the spring equinox? I don't get it.
On the spring equinox.
Wait, the spring equinox is where on the spring equinox? Where would the spring equinox be on this sky?
Wherever the sun is?
Sun is.
Correct. Who said that? Who said that? Who are you? Where are you?
Matt and I said it.
Juan said it too.
Oh, so several of you are good enough to know. I'm impressed. I expected to have to pull teeth for this. On the spring equinox, the sun is on the spring equinox. So the spring equinox is here. So what's the local sidereal time then?
The same one.
Give me an answer.
Where the sun is?
No, I want a time.
Oh.
I want a 24-hour time.
Or plus 12.
False. This is not solar time. We do not start sidereal time at the nadir. We start sidereal time at the meridian.
Oh.
That probably didn't make any sense.
No.
So we have to do 16. No, wait.
Joel, you're overthinking this. Hour angle of the spring equinox. What is the hour angle of the spring equinox right now?
4 p.m.
You don't use PM in sidereal time. It's not 1600, Brendan.
4.00.
You don't use decimals. You use colons.
400.
400 hours. 4 o'clock. It has been 4 hours since the spring equinox crossed your meridian. Since we used a diagram, the way you explain this is you say by inspection. That's how a physicist would say that. They would say by inspection, meaning I drew a picture and that's how I figured it out. Keep in mind, sidereal time starts up here at 0 o'clock and goes all the way around to 24, all right, or 23:56, whatever you want to call it.
What's at the bottom? That word that starts with an N.
The opposite of your zenith is known as your nadir. The reason why I mentioned it is the reason why people got screwed up. The reason, for instance, why Brendan said 16 o'clock is Brendan is used to the sun starting down here at the nadir meridian, and we usually define that as midnight or 00 hours. Then we go 12 to noon, and another 4 would be 16. But what Brendan is forgetting is that when we keep time by the stars, we don't mark the spring equinox down here as the start of the day. We mark the spring equinox crossing your zenith meridian as the start of the day. It's only been 4 hours since it crossed your zenith meridian. That might have been a little too much vocab for you, but I tried. Who cares? It's just a fancy vocab term. Let's try part B. Part B says, the local sidereal time is 1930. When will Vega, a famous star, cross your meridian? Let me give you some help with this one. The local sidereal time is 1930. We want to know when will the star Vega cross your meridian? They were expecting for you to solve this problem by looking up the right ascension of Vega. There's a sample problem in the text where they give you the right ascension of Vega is 18 hours and 35 minutes. To solve this problem, we're going to use the legendary formula Ha equals list minus Ra. The LST is 1930, the right ascension is 1835. We're going to stack them vertically. 1930 minus 1835. Try to keep your hours and minutes separate here. Does anyone know what the subtraction of those two are?
Uh, 55 minutes.
55 minutes. Let's see how Joel did that. 19 minus 18 is, sorry, positive 1 hour. 30 minus 35 is negative 5 minutes. If you have 1 hour and you take away 5 minutes, you get 55 minutes. However, this is not the answer to the problem because the hour angle tells you time since the meridian. And that means Vega crossed 55 minutes ago. In other words, Vega's probably somewhere up here right now. When will Vega cross next?
In 23 hours and 5 minutes.
Very good. Because if you do 24 hours minus 55 minutes, you get 23 hours and in 5 minutes. And that's the answer to our problem. We got one more part to do, guys. Stay with me. Don't die on me now. Cam, you give me a thumbs up when you're ready to go. I want to erase now. I'm erasing. C. You observe a star that has an hour angle of 13 hours. The local sidereal time is 8:15. What is the star's right ascension? Let's just use the formula for this one. Our angle is LST minus RA. Do you guys know how to solve this for right ascension, how to rearrange this formula?
Does RA go to the other side, summing it?
That's right.
Summing
So
with HA?
plus RA, right? And that takes the R away from here. Then what do I do? Now I have RA plus HA equals LST.
Back to HA.
Yep. To get RA equals LST minus our angle. So we're going to do this minus this. This is a little bit tricky here. Do 8 hours in 15 minutes minus 1,300 hours. All right, what should that equal here? Anyone think that?
5 or minus 5?
All right, yeah, let's keep them separate. Juan's got the right idea. 1 minus 5 hours, but how many minutes?
That'll be 15.
Positive 15 minutes. But now you have to glue negative 5 hours and positive 15 minutes back together. What does that give you?
515.
No.
515.
Nope.
445?
Yes. Negative 445, right? Because you're minus 5 hours and then you're adding 15 minutes to it.
Oh, I get it.
But hold on. Right ascensions are defined as your hours east of the spring equinox. This negative means this is that many hours west of the spring equinox. We should convert this back to a positive RA. How would I do that?
Add 24
Yeah.
hours.
So do 24 hours minus 445. What do you end up with?
$19 hours and 15 minutes.
Good. I was wondering if you get that. 1915. And that's your answer right there. Those problems can get real tricky, guys. Once you've solved a few of them, you kind of get the swing of it, but first times you do it, it's a little messy. You said it, Alex. Look, guys, I'm burnt too. That was a hell of a homework. The homework would have gone smoother if I hadn't covered the moon today, but the good news is because I've done the moon, the next set of lectures are actually going to be a little more elegant. So I paid it forward today. Now you guys are going to submit this stuff as soon as possible, correct? Please submit it vertical, right side up. Hopefully I'll be able to see the image. Okay. Juan's already taking pictures.
Brendan, can I see what's under 13? Like the 13. There you go. Thank you. Okay, I'm all set.
All right. Do you mind if I send it a bit later?
That's fine, as long as you promise to do it. Don't try to send it to me Sunday night at like 11 p.m.
Yeah. All
So-
right. Have a good one.
Gomes, no problem. Take care.
Can you forward me that picture?
Oh, right.
Thank you.
Let's see here. In my email, Cam sent that.
That's me.
There you are. Okay, so there's the pic.
Is that a good picture or?
That's great. Save
Okay, good.
image as.
Just forward the whole email, Brendan.
Well, then I'll have to look up. I've got a better idea. What was that number? That was number
Does I think it was, look.
41EF.
Yeah.
I'm gonna save that to desktop. Rather than forward the email, because it'll actually be faster to do it this way. All right, so now I'm gonna go to my chat. I'm gonna go to everyone, file, come on baby, desktop.
This was homework number 2, right?
S1.
Homework 1?
S1.
But Joel, the chapter is S1, but this is homework number 2.
Oh,
that's a good point. So guys, everyone make sure that you write down, I should have done that. This is homework number 2. I should have thought about that. Thank you, Juan, for catching that. I should have said that. Okay, Ava, catch you later, alligator. What about Kelly? Did you get that picture? Yeah, see you, Ava.
To the chat?
Yeah, I sent it to the chat as a file. Do you see it?
No.
Oh, bloody.
Wait, I see it now. Never mind. I see it.
Okay, all right, all right. Okay, the twins are hard at work submitting their homework. Anything else, guys? I think that about wraps it up. That was a hell of a day today. I promise not all the homeworks will be that bad. Yes, okay, I know. All right, I'm gonna stop the recording and I'll see you all on Monday, 11:30, okay?